All right. Well, good morning, everyone. Let me add my welcome to what Professor Law would have said yesterday. We're glad to have everyone back in person on campus and see the people actually here physically in the building with smiling faces and things like that. That's the biggest difference, I think, between now and before the pandemic. Everyone's always smiling in class. It's fantastic. They're just like, thank goodness this isn't on Zoom there. So this morning, it's really a pleasure to introduce Professor Ron Hanson. Ron is the Woodard Professor of Mechanical Engineering at Stanford, where he got his PhD and has been ever since. And I think without question, Professor Hanson is the world's leader in the development of quantitative laser diagnostics, their application to combustion chemical kinetics, and then the use of shock tubes to probe those kinetics. I don't even know where you would begin about talking about the things that he's done over his career, the accolades he's won, et cetera. Just to name a couple, there is the gold medal winner of the Combustion Institute. He's a member of the National Academy of Engineering. And I think one of the true distinctions of any academic is the impact he has not on the research only, but also on people. And he has students literally everywhere. You can literally go to just about any university in the country, any company, and you'll see his impact on the people and then the subsequent impact that they make. On a personal note, I know that you're all in for a treat this morning. When I was a graduate student at Stanford, I had the opportunity to take 2 graduate courses from Ron, and I distinctly remember at the end of the course about experimental methods, he said, oh, that's a pretty good presentation, especially for a computational person. So I don't know if that's true. I'll just pretend it's true or embellished or what have you there. But I certainly learned a lot from him about something that's really quite removed from what I do on the computational turbulence side of things there. And I think my perspective on that is certainly due to Ron himself. So without further ado, I'll turn it over to Professor Hanson. I hope you'll welcome him along with me this morning.
So welcome to the short course. That reminded me that when Mike was in my class, well, anyway, what I'm going to present is everything we did in a full quarter, but I'm going to do it in less time. So what does that mean? You know, speed is distance over time, so I'm going to have to move fast. So my philosophy is going to be to move a little bit fast. You're going to see some things. Maybe there's something you're going to like, and you're going to have to study a little bit more. So you're not going to be able to, well, some of you are pretty smart, so you might be able to learn this faster than I did. So this is my plan. This is supposed to be about laser diagnostics, but laser diagnostics have to have applications. And so I'm going to talk to you about applications that mostly involve chemistry or fluid mechanics or energy transfer. And the underlying science for laser diagnostics is called molecular spectroscopy. So we'll spend a little time on that, maybe about 40% of the course. Then we're going to talk about 2 particular methods, diagnostic methods, laser absorption and laser-induced fluorescence. And I'm going to try to sprinkle applications throughout the presentation. Shock tubes, engines, propulsion, fuels. Is the mic okay? Is it loud enough? Okay, good. Well, Princeton's a beautiful place, but so is San Francisco and Palo Alto. This is a picture of the campus at Stanford. This is the central church. My office is in this building. My lab is a little bit off the screen. So it's a beautiful place too. It's in the Spanish style rather than the New England style. And you would have seen the Golden Gate Bridge. So that's the other highlight of where we live. All right, this is lecture 1. There's 15 lectures. Each one's about 45, 50 minutes long, I hope. I'm going to do some overview material first, and then we'll get into the meat of the course in the latter part of this lecture. So this morning's lectures 1 through 3. What are the objectives? I'd like to introduce you to the fundamentals of molecular spectroscopy. You won't master it, but you'll at least understand the foundation on which laser diagnostics are developed. I want to introduce you in particular to laser-induced absorption and fluorescence, which are kind of the starting point of laser diagnostics, and they happen to be ones that are very quantitative. And I'm going to introduce you to shock tubes as a way we produce controlled high-temperature gases. Shock tube is a heater, and we can use that heater to study a lot of different things that involve high temperatures. I've updated my course in the last year or two trying to relate more to energy, so we use the word combustion, but it's really reactive systems. Reactive systems for engines, reactive systems for energy transformations. I'm going to sprinkle diagnostics applications throughout relating to propulsion flows and engines, a lot of shock tube kinetics, and finally we'll end up with fluorescence imaging. So what do we mean by spectroscopy? Spectroscopy is really the interaction of radiation with matter, in our case gases. Here's a couple of examples to get you started. So the upper right-hand plot is a plot of the fractional transmission of light, monochromatic light, as it's tuned in wavelength or frequency across this region. This is hydrogen bromide, 1%, 1 atmosphere in a 20 centimeter cell. So what do we see? We see as we scan the laser in frequency, we find features, and these features are called lines. And these lines sometimes combine themselves into branches, and branches may combine themselves into systems. So there's a lot of terminology in spectroscopy, but it's all based around the idea of finding molecular wavelengths for which interaction occurs, and we can measure it and use that to quantitatively probe the gaseous flow. Now I should introduce the frequency units. In spectroscopy, we talk about frequency. It's an energy unit. It's 1 over wavelength. It's the number of waves per centimeter. So if you've done the math, you'll know this is 4 microns of light, 4 microns right here of wavelength. Now, if we blow that region up and look at one of those small features, only now we're going to do this in nitric oxide at 600 Kelvin, you'd see that one of those features now looks rather broad. So we begin to realize the power of lasers is to probe the structure of a line, shape of a line, not just the fact that absorption takes place. So there's benefits to doing this that I'll talk about later. Now, why would we care about lasers? The lasers are bright, they can be monochromatic, they're coherent, so they propagate into a high temperature gas, and because they're brighter than the gas, we can probe that system and overcome any net background emission that might be present. This enables us to do a variety of different diagnostic methods. LIF stands for laser-induced fluorescence, Raman spectroscopy, laser-induced incandescence, particle imaging velocimetry, CARS, that's coherent, anti-Stokes Raman spectroscopy. I'm going to focus mostly on absorption and fluorescence because they're techniques that can be made quite quantitative and beneficial. Now let me show you how sensitive they can be. So these lower left-hand plots are plots of the detection limit in parts per million for different species. So you'll see there we've got some, I'll call these small molecules. And you'll see that if we have a 1 atmosphere experiment with a 15 centimeter path length across my shock tube, megahertz time response, we can detect in the range of 1 to 100 parts per million of those species. But if you look at the next plot over, you'll see that it's about 100 times better. So when you go to a reactive radical, a small diatomic radical, OH, CH, CN, NH, and so on, we can actually detect subparts per million with microsecond time resolution in an absorption experiment. And we can do it very, very quantitatively. Now I'm going to talk about the role of lasers, just very briefly. I'm going to talk about the role of lasers in energy sciences, and then we'll talk about propulsion, and then we'll talk about chemistry. There's a lot of, I want to tell you about some applications because I want you to be motivated by what you can do with this technology once you learn enough about it. Remote sensing, combustion monitoring, control, environmental monitoring. One of my students also works on medical diagnostics. So it's all the same science. It's only the application and therefore some of the equipment that changes. What are the things we might try to measure? Common goals might be to measure temperature. Temperature is very important in reactive systems. Temperature, pressure, density, velocity, mass flux. Those are common, call them gas dynamic parameters we might need to characterize our system. I'm going to show you a couple of pictures. This was the first laser-induced, PLIF stands for planar laser-induced fluorescence. That's a method that was born in my laboratory, 1981, 1982. That was the world's first planar-induced fluorescence image in a spray flame. One of my students now is a vice president of a company in Boston. Coal gasifier, so that's a real practical system. This is a high pressure, slagging, high temperature, difficult environment. We made measurements. That was at the University of Utah. Swirl burners, that relates to the kind of combustion that would take place in a gas turbine combustor. Coal-fired power plants, student made measurements inside that system, and a variety of different incinerators and process heaters that have been used. So these techniques I'm going to tell you about can be used in a laboratory for fundamental studies, or they can be used in the field. They're practical. So I've had 4 students down at Caltech for 2 weeks making measurements in their hypersonic shock tunnel, the largest university shock tunnel in the country. And so these measurements, these techniques can be quite portable. Now you might ask, what are some of the roles that these diagnostics might play? So we might think about the intersection here of characterizing test facilities. So maybe you have a test facility and you're really trying to quantify exactly how it's performing, and you might, this is an example that was carried out at the Wright-Patterson Air Force Base in Ohio, some sensing, one of my students there, professor at Colorado now, doing TDL, that's tunable diode laser sensing, that means absorption, in a scramjet. So maybe you're interested in characterizing the test facility. You're interested in measuring the temperature, the velocity, the mass flux. Or maybe it's a flow that you don't even quite understand yet, and you just like to understand what's coming out. So here's an experiment probing the exit of a Titan IV at Aerojet in California. This is one in which the student was probing the exit of a pulse detonation engine, developmental engine. Really didn't even understand what's happening inside. That was our first attempt to make measurements remotely, so the student is about 100 meters away looking at this experiment through fiber optics. Or you might be a system that you understand pretty well and you're trying to validate a detailed fluid mechanical model. Here's an example where we were probing a hydrogen jet in crossflow. This was a fundamental flow field for studying scramjets, mixing. This is an IC engine. So we've been probing, right now we have a project with a company in Southern California, a racing company, probing inlet and exhaust. We previously had a contract with Nissan to probe inside the cylinder. So these are techniques that are driven by practical applications that we'd like to get the benefits of lasers to probe inside hostile environments. The good thing is about these techniques, they can be used in a small scale experiment or they can be used in a laboratory. So I've had students making measurements 100 feet in the air or inside extreme conditions. One experiment we were measuring temperatures of 14,000 Kelvin. So these techniques have wide applicability. Now here's an example of the role of lasers in combustion chemistry. So in chemistry, you have a detailed chemical model that you would appeal to. It might be for oxidation of a hydrocarbon. And it's composed of a set of reactions and their specified rate coefficients and some thermodynamics to relate the forward and reverse reactions. So how do we study these things? It's still a fact, my theoretician friend is not here, but it's still a fact that in most cases, a good experiment is better than the theory for predicting a reaction rate coefficient. It's hard to do experimentally, but it's even harder to do this for theory. All right, so how do we study this problem? We make use of a shock tube. There's a constant diameter pipe separated into a high pressure driver and a low pressure driven section. We break the diaphragm. Shock wave propagates down at some speed that we measure. And from that and the gas dynamics relationships that you've probably all had, compressible gas dynamics, if you measure the speed of the wave or its Mach number, you can calculate the jump conditions, and you can calculate regions 2 behind that wave. That wave propagates down and hits the end wall and reflects, and the boundary condition is that the gas is stagnant. So behind that wave, the gas is nominally stagnant. So it's a sample sitting there for up to maybe 100 milliseconds, often only 1 millisecond. And for a short period of time, we have a controlled high temperature environment in which we can measure things. We might know the temperature to 1%, pressure to 1%, and now we have to measure, but we have to measure fast. The kind of measurements we would make are illustrated here. We don't make all of these in any one experiment, but we might be probing this region here by introducing different wavelengths from different types of lasers, infrared, ultraviolet, visible, deep UV. Why? Because different molecules absorb at different wavelengths. So if we want to access nitric oxide right now, we're working at 200 nanometers. That's in the ultraviolet. Molecular oxygen, we might work in almost on the edge of the vacuum ultraviolet. So the species, each species has this unique absorption spectrum. If we understand that, and we're going to spend some time talking about that, if you understand that spectrum, you can calculate the wavelengths you need to use, and you can calculate the absorption coefficient, which would allow you to convert a measurement of absorption back to a useful quantity. So we would probe this with a variety of monochromatic light. In one experiment, we might only use one wavelength. Others, we might use 4. We might also look at the emission of that high temperature gas. That gas might be anywhere from, we do experiments as low as 600 Kelvin and as high as 14,000 right now. We might also look through the end wall. A recent thing is for us to have a transparent end wall and to observe ignition phenomena, other phenomena, with a high-speed camera. Or we might sample. So there's a lot of different diagnostic methods, all aimed at probing that high-temperature environment in which chemistry is taking place. And the virtue of the shock tube is that it has a very well sharp time zero. Shock wave passes, and within a microsecond or so of uncertainty, we'll call that time zero, and the system begins to react. So we have well-determined conditions, good optical access. This could be used to measure ignition delay times, the rate coefficients for elementary reactions, and we might measure species time histories. And I'll show you an example in a minute where we would instead of measuring just one thing, we might measure a family of species versus time, thereby constraining the detailed models that people are seeking to develop. And this is a new one here. We're just starting to look at the use of shock tubes to reform natural gas into hydrogen. So it's really reaction chemistry. You can call it combustion or you can call it energy transformations, but it's basically, we'll use the shock tube to promote this idea of shock wave reforming of energy carriers. We probably measured 25 or 30 different species in the time I've been at Stanford. Sometimes they're radical species, intermediate species, product species, a variety of different species. So it took many years. I started, first laser application in the shock tube was probably around 1972 or so. And at that time, it was a goal just to measure one species versus time. But after a while, we learned how to make measurements of multiple quantities. This is a great example. This is a case where we shock heated heptane, 300 parts per million, dilute in stoichiometric in air, but dilute in argon, 1500 Kelvin, shown on a logarithmic scale. And so we start with heptane C7H16. And what we find is that within 10 microseconds, at this condition, most of that heptane, much of it had been converted to ethylene. So big molecules want to be small molecules. Start with a big fuel molecule, it wants to get smaller, it wants to work to its way towards combustion products, H2O, CO2. What we observed when we looked at this is a bit of a surprise. It was there, we just hadn't seen it. That if you measure, here's OH is a measure of the radical species. It kind of goes up, it goes flat. So if you only measure, say, ignition delay time, this is the time you get right here. When there's a rapid production of OH, that would be a demarcation for the ignition delay time. What you realize is one number for an experiment, ignition delay time, is insufficient to constrain the chemistry that you're seeking to study. So what we began to realize is that by measuring multiple species and asking the model, how well could you replicate all of these different quantities, we begin to constrain that detailed model much more strongly. And that led to an idea that if you look at this, you realize that the fuel, in a hydrocarbon oxidation case, the fuel oxidizes or breaks down by pyrolysis quickly within, say, 30 microseconds, 40 microseconds. And the ignition or the oxidation chemistry takes longer. So the idea was born of thinking about this chemistry as a two-phase process: pyrolysis of hydrocarbons, oxidation of small molecules. And that idea led to something that we call at Stanford HyChem. It stands for hybrid chemistry. Basically a two-phase way of thinking about this, so that we take the very, very complicated pyrolysis chemistry, sometimes represented by thousands of reactions in a detailed model, and we replace that model with a very simple 7-reaction model, which is sufficient. It's empirical. But the point is that model is sufficient to give us the ingredients that go into the detailed small molecule chemistry that's inviolate. We can't change that. Once it's known, it can't be changed. So that concept leads to a much more compact form of chemical model, which can be used in computations of practical systems. So where did that idea come from? It came from the idea that from detailed speciation, you can see that its behavior and it can be modeled as if it proceeds in stages. But the gold standard of chemical kinetics is to measure the reaction rate directly. And those of you who have had combustion courses probably will have heard that the most important reaction in hydrocarbon combustion, in terms of controlling the time in which the combustion takes place, is this branching reaction. H plus O2 goes to OH plus O. One radical goes to 2, 2 goes to 4, etc. And that rate coefficient is the most important one to constrain in a model. And so, as I told you, it's still possible, it's still the case, that the experimental measurements, if done well, are a more reliable source of rate coefficients than the theory. The theory is there, of course. I've had 3 students over a period of time from 1990 up until 2017 who've worked on this particular reaction. And the good news is the results all agree. They fall in a straight line. We think the uncertainty is now driven down to 5–7% maybe. So, but that's taken 30 years to do this, make this work. So that's the gold standard. Once that's done, you don't change it anymore. It's in the detailed model. You might recognize its uncertainty, and in some sort of uncertainty analysis, you might allow it to vary within its uncertainty. But the better we do this, the better our computations are going to be. This is some stuff that's buried in the material that you get. It's just a list of books that you might want to appeal to if you want to dig into this a little bit more. Okay, this is an overview of the lecture series. So we have 5 days, 3 lectures a day. Friday will all be fluorescence. The first half of the course, the first lecture, up to about lecture 5 or 6 or 7, we're mostly going to talk about spectroscopy. What's the terminology? How do you even think about these transitions? How do you think about it for the infrared? How does that differ from the visible and UV? We're going to have that base. Have to have that base before you really can appreciate how laser diagnostics can be quantitative. And my goal is quantitative laser diagnostics. We'll have lots of applications sprinkled throughout. We'll do 2 case studies here for you to see exactly what we have to go through if you're doing something for the first time. If you're just copying what someone else has done in the university, well, then you just have to understand what they did. You don't have to repeat the calculations. You just have to understand them. Okay, now, so we're now starting what I'll call lecture 1. We're going to do some introductory material, talk about the role of quantum mechanics. We'll introduce Planck's law, talk about absorption and emission, which are our primary techniques. And we'll talk about the Boltzmann distribution, which hopefully most of you will have at least heard about. And we'll do some working examples, a number of working examples. This is a picture of, this was probably around 1990. This is what's called a CW monochromatic ring dye laser. Ring refers to the fact that the light follows a figure-8 path in this cavity. So laser is a device in which you send in energy, you convert that energy into a form of hopefully monochromatic light. It might be pulsed, it might be continuous wave, but you send in energy and you convert it into this useful form. So he's adjusting this cavity in which this light is circulating and controlling the wavelength. That would be a ring dye laser, so that means it was pumped by probably an argon ion laser into a organic dye, which fluoresces, and then which is constrained by the optics to only emit at one wavelength. Okay, here we go. So what about the role of quantum mechanics? So quantum mechanics is the basis of molecular systems, microscopic systems. So what do we really need to know? We need to know that atoms and molecules have only allowed quantum states. They don't have a continuum of internal energies. They must exist in quantum states. So that's important. If they exist in quantum states with well-defined energies, and if the transitions of absorption and emission are between states, that means that's the basis of the spectrum. So but if we accept 2 or 3 rules from quantum mechanics, You never have to take a course in quantum mechanics. My students all do. But we can keep this really simple. And it's amazing how far you can go with a mechanical model of an atom or molecule if you'll just accept a couple rules. Now we have this plot here. This is a plot of it's called the potential energy well. This is a diatomic molecule, 2 atoms. It could be homonuclear, meaning that 2 atoms are the same, or heteronuclear, they're different. And that reflects the energy that's stored in the electrical interactions of these 2 nuclei as they move towards each other and back. And so, but inside this well, those are the electronic forces, which are all based upon the charges in the nuclei and their spacing. But inside we have the quantum states, and we have quantum states for vibration and for rotation. So we think of the internal energy of a molecule or atom. Well, for a molecule, it is comprised of electronic energy, vibrational energy, rotational energy. So there's 3 types of energy. If we live within this particular well, which reflects the electronic configuration, we only have to worry about the vibration and the rotation. So we imagine these 2 nuclei linked by this massless spring, which represents this potential energy well. Meanwhile, this molecule is rotating. All we're going to do is we're going to have mechanical models with the vibrational energies. This comes from Hooke's law, and hopefully most everyone here has heard of Hooke's law for the restoring force of a spring. And we're going to account for the rotational energy. And then we're going to say, by the way, it's quantized. By the way, you can only transition between certain states. And you're just about done if you'll do that. So we now imagine that we have our molecule. We're doing diatomic molecules really today. We have a molecule that exists in certain quantum states. Energy is always vertical. These horizontal lines just reflect some degree of energy, which might be associated with vibration or rotation or also electronic. And so the quantum mechanics is going to tell us the energies of these levels that are allowed. Quantum mechanics is going to tell us which ones of these levels can talk to each other. You're only allowed to have certain interactions with your neighbors. And so we can have either absorption, in which the molecule goes from this state to this state by absorption of quantum, or it may emit spontaneously. Either way, we're just talking about interactions between allowed states of our molecule. So since we have quantized states, that means that we're going to have discrete values for the transition energies. So now we introduce Planck's law. Planck's law says that the change in the energy, the upper minus the lower, and we always denote the upper with a single prime and the lower with a double prime, that difference in energy is h nu, and this is the so-called dual nature of radiation. That if you want to think about the frequency of an electromagnetic wave, there you are. Or you can think of it as the energy of the photon that's being absorbed or emitted. So you can think about the energy of that discrete photon, or you can think about the electromagnetic frequency. Either way, Planck's law gives us this relationship between the change in the energy and the frequency. Now, if we substitute for nu, we're using the expression C equals lambda nu. You can now get this as hc over lambda. Now have 1 over lambda. That's the definition that I told you about of frequency units in wave numbers. So that's a unit of energy. So Planck's law helps us understand the energies. Once we know the energy of the photon, once we know the energies of the levels, and we take the differences that are allowed. Now, small species have discrete spectra, meaning that we would, as I showed you in the first example, we'd have discrete wavelengths of absorption. Big molecules have so many of these things that they blend together, and they have blended features. So when you're in small molecules, we think about these lines distinctly and separately. Once we have a big molecule, like say a hydrocarbon, the lines overlap and we talk about features. We no longer talk about individual lines. Okay, absorption and emissions. So we can have absorption spectra, we can have emission spectra. By the way, anything absorbs must emit, anything emits must absorb in order to have detailed balance at equilibrium. all processes are microscopically balanced. At equilibrium, the rates of all processes are balanced. That's a very fundamental thing to understand. It's necessary for equilibrium. So if you have emission, you can have absorption. Fluorescence is really the spontaneous emission of light from an upper state. So if we use a laser to pump the molecule from one state to another, then there would be a delayed spontaneous emission. So the fluorescence is a reflection of the absorption, but it's not instantaneous, we'll find. And then there's scattering, which is the basis of techniques called like Rayleigh and Raman scattering. We usually, well, we like to use at Stanford, we like to use monochromatic light. If you have a pulse laser, if it's a short pulse laser, then it's spectrally broader. But if you use a CW laser, it can be spectrally narrow. We'll call it monochromatic. It always has some finite width. And if we have the laser that's monochromatic, we can use it to study the shapes of these features, which would not be possible if the laser was broad. So one standard approach for us is to have an incident light beam, collimated light beam with an intensity I0, propagating through an absorbing gas, exiting with a transmission intensity I sub t. And the absorption that takes place simply removes some of the photons, and therefore leaves with less intensity than it enters. And that ratio, I sub t over I0, is called the fractional transmission. And if we plot that as a function of wavelength, we will see features, which we'll call lines here. And those are the basis of our quantitative methods. We might measure the depth of that line, the depth of this transmission. So absorption would be, transmission is say 1 here, 0. If we plotted absorption, it would be the other way around. So these lines are undergoing absorption, reflecting what? Why do they absorb? They absorb because the incident photon is at a wavelength that corresponds to the difference in energy between two quantum states that are allowed. If we tune the wavelength away from that so the photons don't have the right amount of energy, there's no absorption. We can take advantage of that. So it's the propensity per molecule in a given quantum state to absorb that photon. So if we measure the amount of attenuation of light, we've measured the number of photons that are removed, and we can equate that to the number of molecules, density of molecules that absorb light. Therefore, that's the basis of our species measurement. There's a very famous law that I'm going to derive in a subsequent lecture called the Beer Lambert Law, which says if you have monochromatic light, that this light will be governed by this exponential law that the fractional transmission is exponentially decayed. And that absorption coefficient, which we call absorbance, must be dependent upon the length of the sample we probe, the number of molecules that are capable of absorbing, and their propensity to absorb. So we might reflect that as a number density, and the cross-section, we'll use the word cross-section, basically it's the cross-sectional area of a molecule to block light. So if you've had kinetic theory gases, it's exactly the same relationship that you see when you try to calculate the collisional effects that take place, kinetic theory we call it. And so it's the same thing. Now, if the molecules are small, we'll sometimes use this expression here. It's the same physics. It's always proportional to the path length. Double the path length, you double the absorbance, because you pass through twice as many atoms or molecules. We'll frequently talk about do this in terms of the static pressure and the mole fraction. So this product right here is the partial pressure of the absorbers. And in this system of units, S is called the line strength. It's the propensity to absorb light per molecule or per unit pressure. Now, I like to tell the students that we think about the spectra as positions, shapes, strengths, and shapes. What are the positions of the lines? What are the strengths of the lines? What are the shapes of the lines? Where do the positions come? Positions come about if we have the expressions for the energy in all of these allowed quantum states. And then we impose the quantum rules for which states can interact with each other, and now we have the positions. It takes a little energy, it takes some time to get to that level. We're going to spend some time on this. So again, we're talking about the internal energies and the quantum states of the internal energies, electronic, vibrational, rotational. This red curve, which is kind of a parabola down here, this corresponds, when we go out, the distance between the nuclei. If you pull the nuclei far apart, it's no longer a molecule. As they come together, they begin to be attracted. So this is called the attractive side. This is the attractive side. As the two nuclei come together, and assuming their quantum states, electronic quantum states are favorable, they'll be pulled together by electrical forces. As they're pulled together, they lose potential energy and they gain kinetic energy. So by the time we're down here, they're coming together. When they get down to this minimum of this well, now they're starting to, the forces start turning around and they're starting to be repulsive, and the molecule slows down. So if a molecule comes in, or two atoms come in along this path, they come together, and go back out. So unless there is a collision which removes some of that energy, it just reverses itself. So this is called the potential energy well that reflects that interaction. Inside that well are the allowed quantum states for vibration and rotation. The rotational quantum states are more closely spaced. They represent fine structure superposed on the bigger spacing of vibrational energy. And there may be, in a molecule like this, there may be 30, 40, 50 vibrational levels. And then in between, or superposed on top of that, are the rotational energies. Now, if we look in our spectrum and we pick out one of these features, we would call that a line or a single transition, meaning the linkage between two specific quantum states. We go to the next one over, it's a different pair of quantum states. Sometimes these things group often into patterns like this, where these lines get blended into what are called branches. And we'll have terminology for these branches. For example, these are called R and P. We'll learn more about that later. So they're almost like mirror images, reflecting the transitions between particular rotational quantum states in a given vibrational transition. So then we would call these lines and then bands. Two branches, actually, we would call these. Now we use as a definition delta V. We'll talk about delta V. Delta V is always V upper minus, delta is always upper minus lower. And so for rho vibrational spectra, that means combined rotation and vibrational spectra. Delta V is almost always 1. Where'd that come from? Quantum mechanics. Quantum mechanics tells us that the delta V's of 1 are strongly favored over 2 or 3. They're allowed, but they're much weaker. So this would be the P and R branches, or delta V of 1 transition, which we're going to call the fundamental. We'll learn about that later. However, it is possible to have delta V's of 2, but they tend to be 10 to 100 times weaker, delta V of 3. So some people will study these weak transitions, because these weak transitions, their strengths, tell the physicist something about the structure of that molecule. They might provide information which can be used to adjust their theoretical models and the parameters that represent that molecule. So you probe the molecule with light, and the interaction tells you something about the structure of the molecule. Maybe it tells you what the bending angle is of a triatomic molecule like water. Or maybe it's a linear molecule, and you look at the structure and it'll tell you the rotational energies which reflect the moments of inertia. We'll talk about that in a bit. So spectroscopy is used to study molecules. Engineers like me will use this understanding to probe flowing, reacting systems of some kind. It's all based upon the same fundamental ideas. Now, so the simple thing is to look at a single line, or maybe two branches. But now, what happens when we change the electronic configuration? So the electronic configuration is reflected in a sequence of these potential energy wells. So for example, if we took molecular nitrogen, and if we could take a snapshot of all the energy levels that the molecule has. It doesn't mean they're populated. Just snapshot, what are the possible energy levels? Well, these represent a growing change in the electronic configuration. So something's happening to the electrons. They're changing their orbits. And when you change these allowed orbits, they'll have different amounts of energy stored. And so the spectroscopists have developed terminology for labeling these things. So for example, this one's called the A state. And it has some notation that you'll learn about later. But there's the A state, the B state, the C state. And there's many more. Missing is called the ground state, which is always denoted with an X. So this is called a term symbol. We'll talk about that later. But if you were to take a low pressure chamber of nitrogen or air and apply a voltage until it begins to conduct electricity, you produce a fluorescent light. You'll cause it to emit light. You're sending in electrical energy. The electrons are banging into the atoms and molecules, exciting their electronic configurations. You're pumping them into different energy levels, electronic energy levels. So the ground state is an X, but if we looked at these are some of the low ones of nitrogen. They didn't have names. So if you looked at a nitrogen discharge, you get light at about 500, 600 nanometers. And that group of lines they'll be able to name, it's called the first positive system. So the spectroscopists they've excited atoms and molecules every way you can imagine. And you look at the interaction, and what does it tell you? It tells you about the structure of the atoms and the molecules. And that's the way the physicists attack this problem. This is a cutout from my lab course that I give each year. We do an experiment like this. We take a little low pressure discharge, apply some voltage, starts to emit light, put that light into what's called a spectrometer, look at the spectrum. So we measure the spectrum. And the equipment we use is not that great, so it's not high resolution, but this is what we see. So in the region, your eyes are sharpest around 600 nanometers. Your eyes see between about 400 nanometers and about 750 nanometers. That's where your eyes work. Peak is always at around 600 because that corresponds to the properties of the sun, actually. Evolution. So anyway, this is what we would see in this part of the spectrum between 570 and 610 nanometers with our crude little spectrometer. What do we see? We see a repeating pattern. Repeating pattern. So we'll see, and the spectroscopists have learned, well, that corresponds to quantum transitions of V prime minus V double prime. That means the delta V is 4. But the upper state goes from 6 to 7 to 8 to 9. So we're probing the different vibrational levels within this particular electronic, between these two specific electronic states. And you change the conditions of the experiment, you change the gas, and so you gradually learn from this experiment, looking at emission quite a bit. But our resolution is not very good, so we're buried within each of these things. There's a lot of individual lines and branches. But still, this is the sort of thing you would see if you did electronic excitation of nitrogen. But you might say, well, I worry a little bit about what kind of a discharge this is. It might be a transient spark, might be a steady glow discharge, might be a stream of corona. So the point is, different electric excitations lead to somewhat different spectra. You haven't changed the energy levels of the molecule, but you have excited different, or you've utilized different ones in the experiment. So it might look a little messy. It might look something like this. And so if you did this in air, you might say, well, I can pick out this oxygen atom here. And how did this happen? Over time, the physicists have built this incredible library of knowledge about the energy levels from which you can calculate the spectra. So you observe the spectra to infer about the energy levels. And once you have that information, you can use it for other applications. Basically, this is, here's the UV. UV kind of means less than about 400 nanometers. So there's a lot of action going on in that emission spectrum. Historically, the spectroscopists who started doing this, 100 plus years ago, how did they record the light? Well, common thing was to use film. So you have a device called a spectrometer, which takes the incoming light and it spreads the spectrum, disperses the spectrum. So you take the incoming light generated by something hot. It could be a combustion experiment, excitation. Maybe you capture the light from the atmosphere for a discharge. You distribute the light spectrally, and then you record it. What you're recording is the intensity at each wavelength. So the device is calibrated so that each position in the exit plane of this device is wavelength. And you record the light on film, and then you go develop the film. Then you study the film. And so that's how it's done. And people over time learned how to interrogate OH, CH, NH. So you do an experiment in which you try to constrain the species that are present, look at the spectrum, measure the wavelengths, and then you characterize them and identify them in a way that is fundamental. So people recorded on film, and of course, what do we do now? People now use camera systems, high-resolution camera systems. You don't know how long it took to record the spectrum. These are called, and you can see now why they were called lines, because the light is just spread horizontally onto the film, and it appears like a sequence of lines. And they'd be identified with some notation here. And there's places where it's very, very bright. That might be what's called a band head. So people recorded, the spectroscopists found a way to make the molecules emit, found a way to record the spectrum as a function of position, line positions, from which they get the energy level structure of the molecules, which is, once it's done, it's done. But now we can use lasers. I want to talk about absorption and emissions. So this is a very classical experiment that we do. Take an incident light. It might be a diode laser. We propagate it by fiber, and we emit a collimated beam of light, and it goes across something. It might be a flame. It might be exhaust gas of an engine. It might be a path in the atmosphere. It might be a path across the exhaust of the breath of a baby. We have one like that experiment. Probe the exhaust, the breath of a baby that has a disease, and you can tell from the composition of that gas something about the state of certain organs. In any case, we send the light across, and we measure the amount that comes out, and we form the ratio. So we need the laser, we need detectors, and then the laser's monochromatic, so we have the ability to study the width of those lines. And so, in fact, and this is what really got me interested in spectroscopy a long time ago, back around 1972. And then if you actually could study the shape of a line. I just told you the quantum mechanics tells us that we have discrete, specific energy levels. You get a discrete energy level, take the difference, I get a number. It's the position of the line. But there are reasons, and there are two main reasons. One's what's called the uncertainty principle. Because in these molecular systems, it's in a quantum state. But because it doesn't reside in that quantum state forever, there's always some uncertainty in this actual energy. It's called the uncertainty principle, Heisenberg's uncertainty principle. So there's reasons why these discrete lines actually have some width and shape. And I get interested in this because those widths are actually a function of pressure and temperature. All of a sudden, we have this idea that maybe if I look at the shapes of these lines, we might actually be able to measure pressure and temperature. And we do this. This is the way we measure temperature at, say, 10,000 Kelvin by looking at the shape of one of these lines, which is so-called Doppler broadened. So it's an opportunity. But you have to use a narrow line with laser to do this. And some of the diagnostic methods that are in vogue for combustion or reactive systems are based upon pulse lasers. Pulse lasers, now it's the uncertainty principle again. If the pulse length is short, then it has to have spectral width. But you can't have everything. So, but if you have a CW monochromatic, effectively monochromatic laser, you can study shapes. And that's something we specialize in at Stanford. So there's two key aspects of spectroscopy, really, position, strengths, and shapes. We can study all those. There's something called the Boltzmann distribution, and I'm wondering just how many people know what the Boltzmann distribution is. Okay, it is like extremely fundamental. What does it tell us? The Boltzmann distribution comes from statistical mechanics. And it tells us the distribution, the populations in each of these states. As you change the temperature, you change the relative populations. So another way of thinking about it is it's essentially, this is the Boltzmann equation here. It says the fraction of molecules of a given species in level I, energy level I, the fraction of the total, Ni over N, is given by this simple relationship. G is what's called the degeneracy, which is the number of states having the same energy. So it's the number of molecules that look like they're the same, except they're not exactly the same. It's called the degeneracy. This is the energy level relative to some, you can pick energy level, it's like sea level. You can pick it wherever you want it, but once you pick it, you got to stick with it. So it's the energy of that quantum state above zero. Q is the sum over all of the possible states. So there might be rotational states, vibrational states, electronic states. So Q is the summation. That's called the partition function. What's important is this number right there. What's that? That's the temperature. So this system is in thermal equilibrium, meaning that a temperature is defined. This tells you immediately what the populations of the molecules are in each quantum state. It's like the definition of temperature. So if it's in thermal equilibrium, meaning the temperature is defined, this relationship tells us the fractional population of that species in all of the allowed energy levels. Raise the temperature, you put more up here. Lower the temperature, they come down. But it's like, why do we care? Well, we need this to interpret the fraction of absorption, which is the measure of the number of density of absorbing atoms or molecules. We need this to get the temperature and to get the total number density of that species. This is fundamental. But you can accept it. It's just, it comes from statistical mechanics. And it's a definition of temperature. And so we use this all the time. So if you have a maybe OH molecule, if we probe the number of densities in two states and take the ratio, that's a function of temperature only. So I think, the most accurate way to define temperature, measure temperature in the reacting system. Okay, I'm going to zing along here. I'm going to show you a few examples. I'm going to give you working examples to say maybe this is worthwhile. Maybe you'll relate to one of these examples and you'd like to do something like this. So I had a vision about 20 years ago, I think. Let's take what we'll call diode lasers that you could buy, telecommunications diode lasers. Let's imagine we can buy them in any wavelength or color we want. Let's imagine we can propagate them by fiber, which we can. Sometimes we propagate light between buildings by fiber. Let's imagine we have access to these lasers. We could pass them through fibers. Let's imagine that we could use these to probe the inlet, the combustor, or the exit of a scramjet. And so over time, we have in fact learned how to do this. We've learned how to measure a variety of temperature, velocity, combustion products like H2O, CO2, CONO, oxygen for the inlet. So we've learned how to probe species and parameters, which we test not in a scramjet, but in a laboratory experiment. We validate those, use them there in a larger ground test facility, and then finally they were utilized. It took 35 years from the time we first started doing this, and it was actually used in a flight experiment of some sort of a scramjet. Because these systems can be portable. Now, we live near a place called NASA Ames Research Center where they have the world's, well, I think they're the world's largest arc jets. I'm not sure. Anyway, they have a 60 megawatt arc jet. So, you turn them arc jet on 60 megawatts. It's a pretty big deal. And they use that to test hypersonic vehicle testing of different kinds. It's as you can imagine, there's a lot of, you have to worry about electric signals, interferences. They put this thing in kind of a big box, might be 30 feet by 10 feet. It's an axial discharge called a constricted arc. And so there's an anode and a cathode and heavy-duty water cooling because there's a lot of losses. So the thing looks like a giant nest of water tubes and pipes. And they'll use this to heat air, which they then accelerate. This is basically build up the stagnation enthalpy, expand it into a nozzle, create high velocities and temperature, and test shuttle tile materials. It's thermal testing. It's the main thing. So the question is, how do you even know what's inside? You can do an energy balance probably, but it's limited. So we decided, well, we were asked, is there a way that we could measure the temperature inside, say here, basically the stagnation enthalpy. Could we measure the stagnation enthalpy? We know that it's essentially air. Yeah, but when you expose air to 6,000 degrees Kelvin, 5 or 6 atmospheres, what is it? What's the temperature? So we've been working on this for maybe 15 years now. So we came up with this idea early on that if these conditions, we could probe the electronic excited state of oxygen atoms. So you put in air, you heat it to 6,000 Kelvin, it's not O2 anymore. It's O in its different electronic states. And there'd be some nitrogen atoms, there'd be a mix. But if you've had a course and you've learned how to do chemical equilibrium calculations, you take air and you heat it to 5,000 Kelvin and in 1 atmosphere, you should be able to calculate the equilibrium composition. Well, so I said, it's so hot, chemical reactions are fast. Let's assume chemical equilibrium. So if we measure the population in an excited state, and we use the Boltzmann relationship that I just told you about, what's the fractional population in some excited state? I've just measured temperature. That's the idea. And we did this, and we expected the temperature of 6,000 to 8,000 Kelvin. You know, they're flowing 2,000 amps. They have 2 of these things, 20 and 60 megawatts. And the people who run these things, they really don't want you around. We wanted to drill a hole in the wall and look across. And they don't want that. They have a leak. So the technicians are really, so it's taken us years to get their confidence that we can drill little holes and put in some optical components and measure across them and not ruin their arc jet. So now we're getting a glimpse into spectroscopy here. So we have this is the energy level structure of atomic oxygen atoms. There's different electronic states. We realize that this one here happens to have a transition at 777 nanometers, which is a wavelength for which you can buy a cheap laser. So we took these lasers and we're going to probe this state. And the idea is that we're going to measure the population in this state. The strength of this absorption tells us the number density in this state. And an assumption that this state's in equilibrium in the system is sufficient to give us the temperature. And so we measure the shape of this line, and it turns out that it's not just a single line. There's what's called hyperfine splitting. So there's a number of little lines inside, but they add up. And the integrated area under that absorbance curve reflects what? The number of absorbers. Integrated area is just a number of absorbers. And from that, we get the temperature, and we got 7,130 Kelvin plus or minus 120. How do you measure 7,000 Kelvin? You do not use a thermocouple. So you're probing a quantum state, making an equilibrium assumption, and there you go. That's how it worked. It worked really good. We're still working on it. This is, they changed the arc current. We could actually detect small changes in temperature when they changed the arc current. So we could measure, well, at best, when everything's working, we can measure temperature at about 0.3%. Another interesting thing is, this is maybe 10 years old. PDC stands for Pulse Detonation Combustor. So in the early days, now the people are using rotating detonation engines. Previously, it was pulse detonation engines, PDEs. So this was a pulse detonation engine. So we have some colleagues 75 miles to the south, Naval Postgraduate School, and they have one of these systems. And the pulse detonation engine is you fill it with something like ethylene air, ignite it, detonation wave comes down, flows out a nozzle. You need to work it at higher pressure, so there's a throat. What they wanted to know was, is there any possibility you could use this to drive a gas turbine? And what do you need to know? You need to know the enthalpy flux. What's the enthalpy of gas coming out, the function of time? How do you measure enthalpy? Well, so we thought about it, we came up with this idea. So what do we know about the flow through a converging, diverging nozzle? What do you know about the throat? Sonic. What do you know then? You know something about the speed of, you know the speed is Mach 1. You know the velocity. And if you tell me the temperature, I can tell the speed of sound, which means I can tell you the velocity. So with that simple idea, you could try to get at the what's going on in the system. So we can measure, hopefully enough. We measured CO2 and water, CO, temperature, measured those things. And you put that together. Now, I have two ones that give you a sound. So this is. Our couple seconds. But anyway, I won't play it again. So the point is we're probing that complicated thing. But because it's only that, we don't have to worry about cooling because it's only 2 seconds. So the idea is we're going to measure in this throat of this nozzle right here. We're going to measure all the things we need to know. We're going to use lasers at 1.4 microns. That's a convenient telecom wavelength, 1.4 microns, or 1,400 nanometers. And from this, we're going to get, by measuring CO, CO2, which happen to, these absorb at, well, water absorbs here, but CO is at 4.6, CO is at 2.7. We measure all those things, which means we measure the combustion products, put all that together, we get the enthalpy flux. And we can measure time-resolved temperature. These temperatures are pretty high now. We're measuring, 3,000, 4,000 Kelvin. And comparing this with the Naval Postgraduate School NPS 50. Because, they have codes. Codes aren't perfect. And so they still rely on experiments to try to validate their codes. So the sensor works well even at high temperatures. And I'm sure. So this was a mass flow. We can get mass flow from the density times the velocity. Choke condition, measure the species, mass flux. Okay, finally, this is a plot of the enthalpy flux as a function of time in joules, megawatts or something. So that's an example. I like this example because it shows that if you put together different measurements, you can get things you wouldn't think about. Mass flux, enthalpy flux, thrust, momentum flux. I don't think I'm going to show that. Maybe in another talk, I'm going to show you how we measure the mass flux of air going into a full-scale jet engine. We're measuring the absorption of the oxygen and its velocity. We know it's air, so we can convert that to a mass flux. Now, another experiment. This is called the HEG. This is a shock tunnel in Germany. One of my students, now my staff engineer, took his diode laser system over to this HEG. It's a big deal. 60 meters long. By the way, there's now one of these shock tunnels in China that's 265 meters long. It's unbelievable. And all of this is to get a short burst of very high speed flow that you use to test aerodynamics. Anyway, this is how you test, and this is called an impulse facility. So you live with the fact that for a short period of time with shock waves and so on, you can generate really high temperatures and high speeds, high enthalpies. But you're going to have to make measurements really fast. It's called impulse facility. Even this big one only has 3 milliseconds of time. This is called, it will run a little bit later. So anyway, we wanted to measure what's happening. You're going to see, this is a very short experiment. Oh, here it goes. This is just his phone camera. Well, the point is, it's a very short experiment. All the experiment was done in about 2 or 3 milliseconds there. And so the question is, what's inside? And how does it compare with models? And how can they use this to design the scramjet? This is a representation. This is a physical model scramjet here. Here's the inlet. And so somewhere in here, there's fuel and oxygen mixing. And the question is, what kind of temperatures? I'm going to just show you that what he measured, the student measured. He could measure pressure versus time. He could measure temperature versus time. He could measure water concentration versus time, velocity versus time, and they could compare this against the CFD model. Whenever you have something like this, it's not ideal. There's always some problem. Heat transfer, turbulence, so you really have to validate these models. So these measurements were really important. Okay. I've been telling you about the importance of these species. Here's just an example where this was called methylformate. This is a species right here. And this is a representative ester. And we could measure, by measuring the time histories of the key species, we can get the rate constant. And by measuring multiple species, we could track essentially all of the oxygen. So you feel pretty good when you're tracking all the species. Okay, I'm going to stop there. So what did we do? I tried to give you just a series of applications to get you motivated. I told you about that we need to learn about line positions and strengths and shapes, and we're done with quantum mechanics. Well, no, there's a couple more places where we'll take a rule. We'll take a rule, except quantum states use our mechanical models for molecules to give us the energies. Then we'll find out which ones are quantized. That leads us to energy differences, which is the spectrum. We're most of the way there. Yeah, question?
So a picture of the first lines that were visible, and now we have like the footprints of those models. But I'm just wondering, how did they come up?
Okay, well, so it's like, you'll see how simple our models are actually. So if the molecule is simple, like carbon monoxide, carbon dioxide, water, those molecules are simple. We can quickly get expressions. We can quickly get expressions for the energy levels in terms of, in case of CO, for example, if you tell me the mass is carbon 12, oxygen 16, CO, I know the masses. If you tell me that the nuclear spacing, I know the momentum, I'm done. It's amazingly simple if you can accept these rules. And so, and after a while, once it's done, you know, I know where CO is, CO2, water. Water's everywhere, by the way. Water is, the good news about water is it absorbs almost at all wavelengths. The bad news is it absorbs at almost all wavelengths. So it's always in the way. But you learn over time. You want to measure CO2? Well, you read the literature. It's, the transitions haven't changed. Once they're known, they're known. Like a rate coefficient, once it's known, it's known. Thermodynamics, once the properties are known, they're known. So people specialize in this, and it's in the literature. So it's easy, and you say, well, I'm a flame person. Well, you go read a book on flames, and you realize, well, that's where OH emits, and it doesn't change. Hope that answered your question. Any other question before we quit? I think, okay, one more. Okay. Yes, yes. So the gold experiment would be an experiment in which only one thing happens. Let's just say I could prepare H plus O2. Just imagine that I had a fast source of H and O2. I put them together at a known temperature, time 0. I just watch what happens with time. So the rate constant. Okay, so you do a simulation. Simulation usually means you have a mechanism. So it'll be a model of maybe it's 5 reactions, 10, 20, 100. But the best experiment is one in which only one thing happens. One reaction. One. If you have H plus O2, for example, H and O2, it wants to produce OH. I measure the formation of OH and I'm done. If there's only one thing happening. The trouble is in many cases, multiple things are happening. So you have a model of the chemical reactions. You always have to impose the thermodynamics. Thermodynamics, maybe we'll say it's adiabatic constant volume or adiabatic constant pressure. Thermodynamics plus the mechanism and the time 0, and you just calculate it. And the variable, if you know the thermodynamics, thermochemical properties, the variables is just the rate coefficients. That's the only thing left. So you measure the species and infer the rate coefficient. And once it's done, it's done. Assuming the temperature is defined. There's some subtleties about chemical reactions without thermal equilibrium. Okay, I'm not sure where we go or what we do. Just right now, I think we stop and you go somewhere for your coffee or drinks or whatever, and we resume. We resume pretty fast, so we can take a short break, or if you want, I'll start early and we'll take a longer break. So, which one? Who would like, okay, you can go, or we can stay and I'll zing along, and then we'll take a longer break. 5-minute break. 5-minute break? Okay, 5. Can you hear me okay in the back? Okay, good. Well, we're behind already. What's the answer? I've either got to eliminate some stuff or go faster. So, but my theory is, this is kind of thin. We're not going deep. I want to give you the big picture. And if you're interested in any little part of that, you've got to dig deeper. So the answer is I'm going to have to go a little faster, probably. Let's see here. Okay, so you've seen these potential energy wells. Now you're beginning to get a feeling for what they are. Usually if we're doing infrared spectroscopy, we're dealing with transitions in rotations and vibrations. That's usually in one electronic configuration, usually the ground electronic configuration. So maybe it's carbon monoxide. And the energy level spacing between these potential energy wells is so big, unless you go to high temperatures, all the CO molecules are in this ground well. So you can visualize this as, say, something like carbon monoxide. And with the, and I've interpreted this curve for you for what it means. These potential forces are all associated with electrical charge. So the molecules come together, they speed up, go back apart. And so we're living within this well. And within this well, we have the rotation and the vibration. So we're going to, and now in one lecture, we're going to talk about rotational and vibrational spectra. So this is something that I would usually spend several lectures on. And we're going to learn about the allowed energy states of rotation and then vibration. We'll start with the simple, you always start with a simple model. If you keep it simple, then you look at the results, you can understand them. Then you make it a little more realistic. So we'll start with what's called the rigid rotor model. Then we'll allow for non-rigid rotation. Okay, so why does a molecule absorb or emit light? A simple way to think about this is if you have a molecule like, say, HCl, which is a diatomic molecule that's oscillating away, it's like a little antenna. If it has a dipole moment, meaning that there's more charge on one end than the other, this thing is just like a little miniature antenna. So the antenna is the thing that can radiate signals, electromagnetic waves, or record. So it's basically like a little miniature antenna. But because of the quantum nature, it's a miniature antenna, but it only absorbs or emits light at specific wavelengths, in contrast with a classical antenna. So if the molecule has a dipole moment, there will be the ability to absorb and emit light. Now, what if it's a diatomic molecule like N2, which is homonuclear? No dipole moment. Because there's no dipole moment that is stretching, it does not absorb infrared light or emit. Quantum states exist, but it doesn't. So we have to think differently about how we interrogate the energy level structure of a homonuclear. So we resort to something called scattering. So we might bring in a photon of frequency nu, frequency nu, and it comes in and it hits this molecule. What can happen? It can be scattered, or it can be absorbed, or it can pass through. If it's scattered, we call that we characterize it as either an elastic or an inelastic process. An elastic process is one in which the quantum states do not change. So there's a collision between a photon and a molecule, so that we have conservation of mass and momentum, but there's no change in the energy structure. That's called an elastic collision. And you might have encountered this if you had a course in kinetic theory for gases. But in addition to elastic scattering, you can have inelastic scattering, and that's shown on the right. In this case, the photon comes in and is scattered, but it goes away at a different frequency. And then that means by conservation of energy, the molecule either got or gave up energy. Conservation of energy. That means that this molecule goes, now if, and this is called, inelastic scattering is called Raman spectroscopy. If the molecule goes down in energy, that means the photon went up in energy. The anti-Stokes photon is greater than the incident frequency. So there's two possibilities. Quantum states go up, quantum states go down. Photon goes down, photon goes up in energy. So there is that type of spectroscopy which we can use to characterize the energy level structure or measure molecules. Remember, we were talking about positions, strengths, and shapes. Right now, we're going to spend some time on positions. Line position is nothing more than the difference between the energy levels, and what determines the energy levels, where we have to have a model for the energy superposed with a quantum mechanics rules. So my approach is we develop a mechanical model, we impose a couple of rules, we're done. You don't have to do the theory yourself. So remember, internal energy, we're talking about internal energy. electronic, vibrational, rotational. But we're going to be focusing now in this hour on rotation and vibration. So here's our molecule that's rotating around. Pick carbon monoxide. It's got a dipole moment because there's a different amount of charge on one end than the other. And it's rotating away. And so if you look at it, you would see like this antenna going up and down, radiating. You can think of it as radiating, or you can think of it as absorbing. So if I looked at the dipole moment, I could imagine that it oscillates up and down, and that the dipole moment does this. And therefore, it has the potential to interact. Well, what frequencies will it interact at? Well, it depends upon on the speed and the properties of this molecule, which we're going to see is very, very simple. Now, just like we said that molecular nitrogen doesn't absorb or emit in the infrared, it also doesn't absorb or emit due to rotational spectra in the microwave region. So molecules are either homonuclear or heteronuclear. They all have spectra, but they don't all have vibrational spectra. We'll see. So there's a way to study everything. Now here's the vibration. It's the same idea. Now the thing is just oscillating. So it's oscillating like a little antenna, and therefore it has a propensity to absorb or emit light at some frequency. That depends upon the properties of this molecule. The properties now, which can depend upon the masses and on the spring constant of that molecule. So we have infrared. If it's heteronuclear, it's infrared active. If it's homonuclear, it is not infrared active. And so you might say, how do we study that molecule? So, for example, if we have a linear molecule CO2 and it stretches, there's no dipole moment. It's there, it's stretching, it's got quantum states, but it doesn't emit or absorb light. But it'll do something. There's always a way to study it. So energy levels are discrete. Optical layout transitions occur, and therefore the absorption and emission spectra are discrete. So why do I say discrete? Well, because quantum mechanics tells us you only can have discrete energy levels. You can't have continuous distribution of energy levels. We're going to talk about rotation and vibration. The simplest models are called the rigid rotor, which just means that we assume that these nuclei have a fixed spacing. And then the simple harmonic oscillator, which says it's going to oscillate, but it's going to obey Hooke's law. The improvement on this is called the non-rigid rotor and the ion harmonic oscillator, which we'll touch on briefly. We'll start with rotation. So here's what I mean by my mechanical model. So we imagine we have these two nuclei with a fixed spacing, R1 plus R2, on a frictionless plane, and it's going to be rotating. So you go back to your courses in mechanics, and how do you analyze this problem? You don't know about quantum mechanics. How to analyze this problem? In a problem like this, you always find the center of mass, and then you ask about the rotation about the center of mass. And this molecule can rotate about two axes. It can rotate about the internuclear axis, which is called the A axis. But there's no mass rotating around that axis, so we don't think about that. But it can rotate about the so-called B and C axes, which are just orthogonal. So you find the center of mass, and you recognize that this thing can rotate about those two different axes. You assume point masses, because the diameter of the nuclei is really, really small. You assume that the spacing, RE, which is R1 plus R2, is a constant. We can fix that later. And so what do we know from classical mechanics? You find the moment of inertia, summation of m sub I Ri squared, which can be written as mu Re squared, where mu is called the reduced mass. It's a way of converting a two-body problem to a one-body problem. That's all it is. So you're finding the moment of inertia about that center of mass. Now, actually, in quantum mechanics, the real rule is that it's the angular momentum that's quantized, which leads to the energy being quantized. So the way you think about this is, well, classical mechanics, I know what the moment of inertia is. Now I take a rule from quantum mechanics. Angular momentum, which is I times the rotational velocity, is quantized. That angular momentum has to be J plus 1 times h bar. H bar is h over 2 pi. H is Planck's constant, a number. J can be 0, 1, 2, 3, 4, 5. It's a number. Those are the only allowed angular momenta because it's a quantum system. Now you look at the energy. Energy is 1/2 I omega squared. You write that out, and you can convert this now into. Now I recognize that since I omega is quantized, I now have an energy expression. The rotational energy has to be this number. H, constant, pi, a constant, J is a quantum number. It can be 0, 1, 2, 3, 4, 5. And I can use my classical mechanics model for I. I'm done. These are the energies that are allowed for this rigid rotor molecule. J can be any one of these numbers. Now what happens? When J gets big, energy's big. Now energy's big. Well, I've got to go back to my Boltzmann distribution. But energy's really high. There's no molecules have that energy. So there's an energy, average energy, which will tell you what the average value of J is in this spectrum. Now we like to work in these units here. We like to work in wave number units. So I have to divide this expression here by HC to get this into wave number. So in its convention, the rotational energy is always written as F, capital F, function only of J. Rotational energy is capital F. Vibrational energies can be capital G. It's just the way it is. F is only, for this molecule, F is only a function of J. I know I, this is called the rotational constant here. H over 8 pi squared IC is called B. It's called the rotational constant. What are the units? Well, wave numbers, centimeters minus 1. It's called the rotational constant. A few little things here. So what does this mean? It means if I know the molecule, CO, I find the internuclear spacing, calculate the moment of inertia. I have everything I need. You tell me J, I tell you the energy. It's done. So it's going to look, now, I bypassed quantum mechanics. Quantum mechanics rests on something called Schrodinger's wave equation. And in this equation, you have not only the constraints, which will tell you which states are allowed, it also can tell you which ones talk to each other. That's called the transition probability. So you can calculate the probability of going from one J to another. And some will not be allowed. So we have to use quantum mechanics at least a couple ways. One is to accept the discrete nature and the quantum numbers that come with that. Next one is to accept the transition probabilities. We'll see. And this all comes back to the wave theory and the role of the dipole moment right here. This is the key in this expression here. What is it? Okay, now, so what's the result? Quantum mechanics tells us for my rigid rotor that delta J, which is always upper minus lower. So if it's absorption, it goes from lower to upper. If it's emission, it goes from upper to lower. But delta J is always 1. The literature is not uniform on this, but this is the way I like to do it. It's simpler this way. Okay, selection rule is 1. That's pretty simple. What does that say? I don't care what your J is. You're only allowed to change by 1 when you absorb or emit light. J of 7 goes to 6 or 8. It's pretty simple. We accept it. Now, since F is this simple expression right here, that says that only any allowed transition between J of 0 and 1 is 2B. So 2B is a number. It came from the moment of inertia. Tell me the molecule, tell me the moment of inertia. I calculate B. I can tell you where the spectrum is. Done. So let's look at this. If we have, here's the energy expression up here. So as J goes up, F, the energy goes from 0, 2B, 6B, 12B, 20B. Now, if you take what's called the first difference, that's the difference between F. Those would be the energies of the emission or absorption. Delta J is allowed as 1. So there's going to be a transition at 2B, and there'll be another one at 4B, another one at 6B, another one at 8B, over here. 2B, or this one from 1 to 2 would be 4B, 2 to 3 would be 6B. That's interesting. So I can take, then I get clever and I can take the second difference between, they're all 2B. What does that mean? That means that the spacing of the lines in my spectrum, 2B everywhere. Very simple. So I can take this general expression and I can solve then for the wave numbers for a given transition, J double prime to J prime, and it's just J double prime. So this is an expression for all of the lines in the spectrum. Positions, not strengths, because strengths have to depend upon the Boltzmann distribution of energy of population in these states. But the positions is really simple. What does the spectrum look like? So here we are. Here's the energy levels here, the transition energies. So there'll be a line here. Here's the one from 0 to 1, 1 to 2. Here they are. And if you map them out, this is the transmission here. This would be the absorbance down here. Absorption is 1 minus transmission. So what does that mean? That means if I looked at this particular one, I'd find that the strongest one here is J double prime of 3. Well, if I honor the Boltzmann distribution, I can calculate the probability of, of fractional population in that state. It depends only on T. I just measured T. This distribution is a reflection. This distribution is a reflection of T, the relative populations. Okay, so the nice thing about this model is that all the lines are equally spaced. You just look at it and you know what to look for. They're all equally spaced. Now, it turns out that the value for B, for CO, is about 2 wave numbers. And you might ask, well, how does that wave numbers don't mean much to me? Can I think about this in terms of a temperature? So the conversion between wave numbers and temperature is HC over K times this, so 1.44. So there's a simple rule that I'll expose you to that kind of relates this back to temperature. Okay, so the line spacing is 2B. And so if I measure the line, take a spectrum, and I do this in my lab, well, the students do this in my lab class. They measure the CO spectrum. They get the spacing of 2B. They solve for the, they know the masses, carbon-12 and carbon-016. They solve for the internuclear spacing. And it's amazingly accurate, even in my little lab class with cheap equipment. You're measuring distances which are amazing. The B corresponds to 1.92, 118 wave numbers, which they measure. Well, they measure it to about 3 significant figures. You can convert that to the spacing, so you're inferring the spacing of these 2 nuclei down to the 10 to the minus 16th meters. But the most important thing is the classical mechanics model with 2 results from quantum mechanics, and I've got my spectrum. Now, I use a simple argument. I call it the equal probability argument. It's just an approximation. It just says that the probability per molecule absorption or emission is simply the population density of that molecule. That is, the relative intensity just reflects the Boltzmann distribution. And that, therefore, the probability per molecule in any quantum state is the same, but there's more molecules in certain quantum states. That's not exactly correct, but it's a good way to think about things. So basically that says, here's the Boltzmann distribution for rotation. Fractional population in J. Remember that was G, that's the degeneracy. The degeneracy is 2J plus 1. Statistical mechanics will tell me that there are 2J plus 1 states that have the same energy. So we lump them into something called the level. So that's the physical meaning for this 2J plus 1. And the rotational partition function is something T over theta R. Okay, so E over K can be written out this way. And I can substitute HC over K, which is a number of 1.44. times B. So if you tell me B is 2 wave numbers, the characteristic rotational temperature is 2.88. So that, the energy level spacing, that's kind of a small temperature. Whereas if we do this for vibration, it's 2,500 Kelvin. Already you start getting feel. That just says these energy levels that have small temperature spacings are going to all be populated at room temperature, or many of them. Whereas for vibrational energy, these spacings are so big that at room temperature, they're only in V equals 0. So there's a reason to why you want to think in terms of characteristic temperatures. Okay, now, one interpretation of this residual degeneracy is that if you took a course in quantum mechanics, you would find out that if you have a molecule like CO in a rotational state, energy state J, there are 2J plus 1 possible orientations if there's an applied field in the problem. We don't have any applied fields in our problem. Therefore, we just have to count these as states that we can't resolve. So there's a physical interpretation of that number, of that parameter, that we always have 2J plus 1. So the partition function, if you've had physical mechanics, you would know this, is KT over this number. It's, okay, now, in statistical mechanics and in quantum mechanics, you have to worry about symmetry and how many ways you have to count things to be discrete states. So the formal partition function for a diatomic rotor is KT over, T over theta R with a sigma, and that has to do with the number of ways that you can rotate this molecule and it looks the same. If I have CO and I rotate it, it looks different. If I have nitrogen and I rotate it, you can't tell the difference. So I have to recognize that as I count states. It's all about statistics that come into play. That's just a microwave active, heteronuclear, sigma's 1, nitrogen's 2. It's all about counting states in quantum mechanics. Okay, intensity. So here's my characteristic rotational temperature, 1.44 times B. Where did I get B? It's just a moment of inertia. Here's some species and what the numbers look like. Oxygen 2.1, nitrogen 2.9. Sometimes molecules have low values of theta R. But these numbers are so small that this means that there's not much energy difference between different J's. Therefore, you're going to have multiple states populated even at low temperatures. So if you haven't had statistical mechanics, this may look a little foreign to you. If you have it, you'll realize this is master's level stuff. Now, it's interesting you ask the question, well, which state has the biggest population? What J? So you can take the derivative of that fractional term with respect to J, and you can solve for the J that has the maximum concentration. And it's a function, as you'd expect, of T and theta R. So if you look at the distribution in emission or absorption, and you see the peak, you could solve for temperature this way if you wanted to. Now you might ask, well, I'm a little confused. What about isotopic substitution? What if instead of carbon-12, oxygen-16, I look at carbon-13? Because the natural abundance of carbon-13 is about, anyway, 1%. Yeah, 1%. You buy a bottle of carbon monoxide, 1% is carbon-13. That's, so the question is, how does the spectrum change between carbon-12 and carbon-13? Are they the same? How do we think about that? Well, remember our classical mechanics. It's just B. It's just the moment of inertia. So I look at this ratio of the B's. It just reflects the differences in the moments of inertia, and it turns out that this is the ratio here. So if you knew this one, you can look at the spectrum and measure the B and infer the mass of that other atom and find out that it's 13. That works pretty well. Now, I want to remind you that the spacing of these nuclei depends on electrical forces, not on masses. So what I just told you is, if I go from carbon-12 to carbon-13, it has the same spacing. Electrical forces haven't changed. That's an important idea that you can use to advantage sometimes. Okay, so now what happens? We want to relax our rigid rotor approximation. It's rigid. As it rotates faster and faster and faster, centrifugal forces wants to make that R a little bit bigger. Of course, if R gets bigger, the moment of inertia changes, which means B changes. So the correction from a rigid rotor to a non-rigid rotor is to recognize that B can change a little bit. And so it changes for two reasons. It changes due to this centrifugal distortion. As you go higher in J, it rotates faster. R goes up a little bit, B goes down a little bit. Also, if you excite it and it's higher vibrational levels, it's got slightly higher average spacing. So the result of all that is we go from the rigid rotor to something that looks a little bit different. A little bit different, it's not much. So therefore, the theory, which the people have developed, the physicists have developed for us, we've got to add a correction term. Here's our rigid rotor term, here's the distortion term, D. D is small, but it's there. But it also goes up with J, now the J to the fourth. So it's all a question of how big is J. But if we do this, now we have a slightly new expression for the energy or frequency in wave numbers of a transition from J double prime to J double prime plus 1. And it has this D term in there. It's small. Let's see, D over B here for nitric oxide is 10 to the minus 6. But I got J squared, J to the fourth. So as I go up in J, this can be observable. Okay, now that simple expression for D, there's a simple expression for D over B that scales with the vibrational frequency. And so that's where we get this number. So now what do? What we do is we correct now B. B is no longer a constant. It depends not only on J, it depends upon V. As you go up in V, vibrational quantum numbers, you have to make a slight correction. There it is, alpha. So as you go up in V, you have to correct B slightly. This is a small number. Now, this reminds me, there's some really famous books on spectroscopy. And Gerhard Hertzberg, Canadian guy, I think he got the Nobel Prize. Anyway, he wrote some of these books back in the 1950s, 60s, 70s. Everybody goes, it's like the Bible. And you read that Bible and you realize, how could anybody be that smart to know all these things or figure all these things out so early on before they had powerful computers? So Hertzberg, Volume 1, is a place where you can find a lot of parameters and numbers that you need. Here's for nitric oxide. Anyway, these are known numbers. So what does that mean? That means if these numbers are tabulated, I can calculate the spectrum. I can calculate the rigid rotor spectrum, or I can do the non-rigid one. So you don't have to do this. They're known unless you study some new molecule. Vibration. So now I've told you, I showed you earlier, something like this. You'll see a pattern like this. This is carbon monoxide. So you don't yet know it, but 2143 is right here, and that corresponds to 4.6 microns. So now what we're finding is that when you look at in this region of the spectrum, 4 microns, you see this pattern. And these are what we call the branches. If I just look at one of these, you might think this looks kind of like the Boltzmann distribution. And that's what it is. But gee, this one does too. And that's what it is. They're just kind of almost like mirror images of the Boltzmann distribution that come about. Okay, now how do we what's our simple classical model for vibration? We had one for classical mechanics for a rigid rotor. But now we imagine that we have two masses, M1 and M2, connected with a massless spring. So you can imagine the thing sitting on a frictionless plate and it's sitting there. I pull it apart and it's going to oscillate. The equilibrium position is that position in which these electrical forces are balanced. You pull it apart, it wants to come back. You push it together, it wants to go back. All because of these electrical forces. Now, we're going to do the same thing. We're going to take a classical mechanics model, and then we impose quantum mechanics. So what do you know from two masses in a spring? If you had a course in classical mechanics, you would say, well, the entry-level law is called the linear force law. But the restoring force depends upon the distance that you pulled it away from its equilibrium position. If you extend the spring, it wants to pull back. If you compress the spring, it wants to push back. And when you solve that problem, classical mechanics, you don't have to know anything about quantum mechanics. If that's a Hooke's law, linear force law, and there's no friction in the problem, it will oscillate forever at a given frequency, omega. And wave numbers is nu over c. So it depends upon what the spring constant k, the reduced mass. And it'll oscillate forever. So that's because there's a frictionless system. Now, potential energy for a spring is 1/2 k times its extension. So that's just the energy that you store. So you pull this thing apart, you've put in some potential energy. And it goes to square, so it's the same whether it's compressed or extended. Okay, so this would say that if I have my classical mechanics model, that the potential energies are anywhere along this red curve versus R. So when it's at RE, there's no potential energy. If you pull it up to, say, here, it's got that much potential energy. Now, when you let go, it'll go zinging down here, pick up speed, and go back up to here, and it'll just oscillate back and forth. But now we need quantum mechanics. Quantum mechanics tells us, no, we have to have, we can only have quantized energies. And by the way, it's going to tell us that it's not exactly a parabola like this. It's a slightly modified parabola. So quantum mechanics is really simple. It just says that there's a vibrational quantum number, 0, 1, 2, 3. Here's 0, 1, 2, 3. And there's vibrational energy, G. I told you that we use G for vibration. Is nothing more than omega E, V plus a half. V can be 0, 1, 2, 3, 4, 5. And the selection rule is delta V is 1. So the nice thing about these simple models of rigid rotor and a harmonic oscillator, the selection rule from quantum mechanics is really simple. You can only have transitions of delta V of 1. And the energy is this very simple expression. Omega E, which came from nu vibe, which came from here, depends only on the spring constant. Now, it isn't a real spring constant. It's the parameter that reflects the restoring energy. So you can find tables of K because it acts like a spring. Now, it's interesting. You look at this and say, well, what's the minimum vibrational energy? Well, B equals 0. Well, what does this mean? That says that the minimum vibrational energy actually has 1/2 omega E energy. Doesn't that seem weird? Even at really low temperatures, this thing still oscillate around a little bit. It's called the 0-point energy problem. But it's true. This is reality. That's called the zero energy. Nice thing about the harmonic oscillator is all the spacings are the same again. Rigid rotor, equal spacings. Harmonic oscillator, equal spacings. So you can use that when you're trying to interpret some spectra and figure out what's going on. Now, the correction to this is called the anharmonic oscillator, so you add another term here. And the next one up is omega EY. So you can add terms, but each time you do that, you pick up another V. So as you go up in V, there's increasing correction to this harmonic oscillator, anharmonic oscillator problem. The effect of this is to decrease the energy. So as you go up in V, the spacing gets a little bit smaller. In spectroscopy, there's a lot of terminology. All of the transitions with delta V of 1 could be 0 to 1, 1 to 2, 2 to 3. All of them have then energies. This would be 0 to 1 would be G of 1 minus G of 0. If you have rigid harmonic oscillator, X is 0, it's omega E. They're all omega E. But if you bring in the first correction here, you have to make this adjustment. So now as you go up, 1 to 2 is is 1 minus 4x. Okay, delta V's of 1 are called the fundamental. If you have a delta V of 2, which is quote unquote forbidden, then that's called the first overtone. Delta V of 3, second overtone. So these are the expressions for the spacings. So why do we have a first overtone? Because as you allow it to be anharmonic, quantum mechanics goes from saying only delta V of 1, well, you can have a little bit of delta V of 2. So when you go from harmonic to anharmonic, you change the model in quantum mechanics, and you begin to have some other allowed transitions. But they're usually pretty weak. So for example, 0 to 1 in the CO is 100 times stronger than 0 to 2. Okay, partition function. So again, if you haven't had quantum statistical mechanics, you may not know this, but there's a simple result for the vibrational partition function in terms of the energy levels. Now there's a problem. Problem is that some people use their pick a 0 of energy, the level V equals 0, and other pick the minimum of the potential well. So there's a half of omega E floating around in different models, and you have to be really careful which one you're using when you evaluate the Boltzmann distribution. So that reminds me of an interesting story. I had an undergraduate student who came from Princeton, and who now has a very important position in the government. She came to me for her PhD. She spent I shouldn't have said that. The student spent 6 months finding a problem that in the end came back to using a different 0 energy for the partition function than for the energy level of that went in the Boltzmann distribution. Just a little, so you have to be really careful about energy zeros in statistical mechanics. How big are these vibrational temperatures? Remember, it's just hc over k times omega E. That's 1.44. So the characteristics of vibrational temperature, here's the rotational temperature for O2, vibrational temperature. See, it's quite a bit larger. What is that? And for Boltzmann, that just tells you that there's not very many up here. If temperature is positive, does temperature have to be positive? Temperature is positive in this distribution. The higher levels all have less population from this relationship. But we have lasers, and lasers means we have a population of the excited state that's higher than the lower state. It corresponds to a negative temperature. So you have to think of it in a different way. It's a population temperature, not a physical temperature. So, but in a thermal equilibrium situation, temperature is defined. So these spacings are quite a bit bigger. And you can think about how they vary with properties like molecular weight and harmicity constants and so on. So you can find all this stuff. It's all well known. And you can try to interpret. So basically, if it has a weak bond, long bond, that means a loose spring constant, means a low frequency. So for example, if we take bromine, well, that's maybe not a good one, but it's a heavy one. It has a very low frequency, very slow, which implies a low force constant, big distances, low energy. So you begin to see a pattern of how these properties vary with them. Okay, some interesting conversions here for you if you want to look them up when you need to. They go between force and length and so on. Interesting question. I've got carbon monoxide. I've just told you about the energy level spacing. How many energy levels, how many vibrational levels does a harmonic oscillator have in CO? 5, 50. How would you get it? You take the dissociation energy, divide by the energy level spacing for vibration, and you get the average number of harmonic oscillator levels. The association energy is 256 kcals, and if you did this with our 2170 here, you get a number of 41. But the number is actually greater than 41 because as you go up, the levels get closer and closer together. Well, so it's the number. people who study the chemistry of how does carbon monoxide dissociate. It has to dissociate from a high-lying vibrational level. So people worry about some of these things, the anharmonicity. There's something called the Born-Oppenheimer approximation that says that you can think of these energies separately. That is, the vibrational character of the molecule doesn't know about the rotational character. In a given V, you can have any J. Given J, have any V. So it means you separate the energy so that the power of this is that you can say, well, the total internal energy is the sum of F and G. And then because these energies are separable, when you do the partition function, which is E to the minus energy over kT, you can separate those terms and think of these partition functions as the product of individual partition functions. There's a lot of benefits to this. Okay, the Born-Oppenheimer approximation. I know. Selection rules. So selection rule for the rigid rotor was delta J of 1. Selection rule for the harmonic oscillator was delta J of 1. But what about when it has combined vibration rotation changes? So quantum mechanics shows us a little bit of a curve. It says the selection rule now is that delta V is 1, but delta J has to be plus or minus 1. So the trouble is there's two numbers. You have given V and J, V changes by 1, but J can go plus or minus 1. But it's two outcomes. And that's why we have two answers. We have two branches. Here's our spectrum. Here's the gap. Here's the R branch, and this is the P branch. Both branches have the same J's, but one is the delta J of plus 1, one's the delta J of minus 1. And here's the rule. Delta J, which is, instead of now being always 1, can either be a minus 1 or plus 1. And plus 1 is called R, minus 1 is called P. And so, I would look at this, and this is frequency. I would increasing frequency. This is always, the R branch is always to the other side because it combines V and J change. R is always the high energy side of the so-called null gap. Now here's the nomenclature and spectroscopy. I don't know how it got started. Think about the alphabet, O, P, Q, R, S. Delta J is 0, it happens to be set at Q. 1 is R, minus 1 is P. S. So for reasons I do not understand, it's centered at Q. So if I tell you R branch, you know delta J is 1. P branch, delta J is minus 1. Now that I have the quantum mechanics telling me the energies of F and G, I can calculate the energies of the R branch transitions. The difference in G plus the difference in J. And I can do that, and I can get what's called a rotationless quantum number for just the delta G. I can do this, and so I now have an equation for the R branch transitions. Omega 0 plus this. And if I do the same thing for the R, it's omega 0 minus. So basically, here's the picture. I'm in given J, I'm in given V, here's the R, here's the P. R is always the bigger number. I can also, since I showed you how you get the peak of the Boltzmann distribution as a function of J, now I've got one in the P branch, one in the R branch. I can use that to get temperature if I want to. Okay, so these are the lines. The sum of the lines, sum of all the lines is called a band, but within the band there's two branches. So there's lines, branches, bands. And if you keep in mind, the height of any one of these lines is proportional to the population. There's no molecules in that state, there's no absorption or emission. The more you have, the more absorption takes place. If you use my equal probability approximation, this is nothing more than the Boltzmann distribution plotted on two sides. But when you look close, you'll see the R branch is always a little taller than the P. That's a breakdown of my approximation. So you can improve the treatment. We can put in anharmonic corrections, distortion corrections, B sub B corrections. You can do all of that, and you can just keep making your expressions for the energies slightly more complicated. So if I look at the R branch, Here's the null gap value, and here's the J-dependent term. So there's a delta B term here. So if the B's are the same, upper and lower, all these things go to 0. And I recover the rigid rotor. But as they go up, you can see that log depends upon the sign of this thing right here. There's a plus sign here. I'll show it to you, I guess. You have to be careful about how the B changes with V. And so for the most part, because of when you go up, B sub V prime becomes is smaller. So alpha, this positive term, alpha is a positive number, so the minus alpha is negative. What does that mean? B sub B is always, B sub B prime is less than B sub B double prime, because as you go up in V, stretching it, bigger moment of inertia, smaller B. So this is what it looks like. So I've now plot this thing, transition probabilities, frequency relative to the null gap. Here's the R branch, here's the P branch. And what you see is as you go up, the R branch ones get closer together and the P ones get further apart. So as soon as you see the spectrum, you immediately see this. You can see it right away. So this is sometimes plotted on a diagram. The name of this diagram. There's the name for this diagram. So you can plot the positions of these lines versus J, and you'll see what's happening. With the R branch, they get closer and closer and closer, and they get further and further apart. What happens when you get up here? That's the funny thing. That's called a bandhead. Well, a bandhead. So if you look at this in a magnified scale, for carbon monoxide, you would see as you go up in frequency in the R branch, you eventually to a place where it turns around and goes back. So if you look at the spectrum, it's like a sharp edge. It doesn't happen in the P branch because those lines get further and further apart. So if you have a good enough experiment, you actually can see all of this. Very apparent. Now you might ask the question, what's the J value here? So you can take this derivative, back to J, and solve for it. It only depends upon alpha. Turns out the bandhead is at B over alpha. It's at 106 for CO. So unless you get up to J of 106, you don't see this. It has to be really hot. Am I doing the time? Running late again. Okay, so what have I taught you? I've taught you that I can calculate the row vibrational spectrum. That's the combined rotation and vibration. I can calculate the spectrum, the positions of the lines, if you give me 4 numbers. BE, which would be the rotational constant. Omega E, that's the vibrational constant. X, that's the correction for anharmonicity. Alpha is the correction for B going up in V. 4 numbers, and I calculate the spectrum. If it's rigid rotor harmonic oscillator, I only need 2. But a real molecule, I need 4. Therefore, it's not that hard. You look it up, you calculate it, and it's good. Now, you might ask, well, that's good, but how would I find those myself if they weren't tabulated? Well, I'll show you how you do that. You'd measure the spectrum, and you'd look for the spectrum for the transitions, for the null gap. That's the rotationless transition wave number at which there's no line. I take that number, which is omega E minus 1 minus 2 xe, do this. Now I take the first overtone. So I've got 2 equations, 2 unknowns. I'm done. So there's always a way to do this. If it's tabulated, you can calculate it yourself. If it's not tabulated, you can measure it yourself. There's another approach. You can fit the spectrum. When my students do this in the lab, we'll measure the spectrum. We'll use this notation, this notation here where we introduce M for J plus 1. I run out of my voice here. So you can write these expressions this way, and I can fit the curve, and I can solve for the 4 parameters. There's another method. I like this one. This is called the method of common states. So if you have, you consider a case where you have let's say I go back here. Okay, back. Just want to go back. Okay. if you take the spectrum and you find the lines that have the same upper state, the difference in their energies is this spacing right here. But I can write that spacing in terms of B, the lower state. So I can use common upper states to solve for B of the lower states. I can use common lower states to solve for B of the upper states. So that's a real simple thing to do. Isotope effects. I told you that the spacing depends only on electrical charge. Therefore, what part of the spectrum changes when I change the isotopes? Only that related to the moment of inertia. So I can use that concept to solve for the changes in the frequency. The changes in the mass and changes in the frequency here. Megareals. Okay. Isotope effects. So when you do this experiment in the laboratory, as my students do, we take the spectrum of CO, or see this background stuff. It's due to the isotope effect. Okay, I think I need to move on. I'm running way behind today. See what's interesting here. Hot bands, okay. If you're a combustion person, sometimes you look at absorption or emission transitions between excited states. Those are called hot bands. So if you look at absorption from an excited vibrational level to another one, that occurs in a different place than the transition from B double prime to 0. So you have to think, well, how strong are these things? So you can look at the populations. You can think about the relative populations. What's the fractional population in level 1? It would be remember, the lowest level is V equals 0. What's the population in 1 at room temperature? 0. What's the population at level 1 at 3,000? 0.23. It was a very temperature sensitive thing, these hot bands. And so all the stuff is in the notes that you guys have. I think you all you got this book, yeah. Okay, so I'm going to zip along. Okay, I want to make another point. We talked about the spectrum of small molecules like NO. Here's the fundamental. Here's the first overtone. Here's the wavelength. The first overtone is at half the wavelength of the fundamental. It's 100 times weaker. Water is everywhere. What do we do when we get to hydrocarbons like, say, endodecane? Small species have discrete spectra. Large molecules have blended features, and we stopped talking about lines. We stopped talking about line strengths. Okay, I guess I need to stop so I can get some water. Any quick question? Yeah. Yes. Polyatomics?
Yes. Can we define vibration as a separate?
Yes. Next lecture. But you, yes. It's common, well, not common. It's a fairly common situation that you can have a rotational temperature different than a vibrational temperature. That's thermal non-equilibrium. You can make it happen. It doesn't want, nature wants it to be in equilibrium. But yeah, you can have, if you say it's probably not thermal equilibrium, okay, the first thing you do is, well, I'll assign a different temperature to the different energy modes. And more advanced question is, can you have a different temperature in different vibrational modes? And yes.
And to decide if hot bands will be considerable or not in this particular band, we also compared the temperature with the vibrational temperature of that specific band.
I'm not sure I understood you. The point is you can have, if you want to use temperatures, the first thing you can do away from thermal equilibrium with a single temperature is to say, well, I don't have a single temperature, but I have at least a rotational temperature and a vibrational temperature. Next step is, well, could I have different vibrational temperatures for different molecules in a gas mixture? Yes. Can I have different vibrational temperatures in different vibrational modes? Yes. I mean, these are like degrees of complexity. Or you can go to a situation where temperature is not even defined. Not even defined. We want temperature because we can use the Boltzmann distribution. But sometimes you give up on a single temperature. Yeah, you can have different. Molecules want to be in Boltzmann distributions. Another question? Yeah.
Yeah.
Okay, see, my principle of equal probability says they'd be the same, because I like to think that way. We're going to get to what's called the Ronald factor. And it'll turn out that the transitions are multiplied, in the R branch, they're multiplied by j plus 1, and in the P branch, they're by j. So they don't have the same factor. And the R branch, is the fractional population is j plus 1 over 2j plus 1, and the P is j. So the sum of the R and the P is conserved, but R is always slightly stronger. But it's not much, but it's true. That comes out what's called the Ronald factor. We'll get to that later. But I think as a starting point, it's just the Boltzmann distributions. Then you modify it a little bit. Okay, I need to get some water. Yeah, question?
What you asked about able to get like the object,
Yeah.
will you be able to be spectroscopy data for vibrational?
Yes. So not in the arc jet, because the arc jet is 6,000 degrees, and there's really no molecules left. But if we did this at 2,500, where there's molecules still exist, the dissociation of oxygen takes place. So as long as there's molecules present, yeah, you'd look at, if you could do it, you would look at the emission spectrum or the absorption spectrum, and you could infer the best fit temperature. Oh yeah, sure, yeah. But because of the propensity to be a temperature, we use what I call the two-line method. We just take the relative population of two quantum states, assume there's a temperature, and it's determined by those relative. So basically, the presence, the existence of a real temperature is, we only need two lines. We don't need the whole spectrum. If we had the whole spectrum, you could ask the question, is there a well-defined temperature? If you only take two, strictly speaking, that's a population temperature. Strictly speaking, if I measure just the quantum states, relative populations of two of them, all they've determined is their ratio. It's just the effective temperature for those two states. And especially when you get into plasmas, you get into situations where temperature is not so well defined, especially in the electronic states, they frequently will use the terminology population temperatures. But all the population temperatures become the single temperature in true equilibrium. So there's chemical non-equilibrium, where the species don't honor yet chemical equilibrium. And then there's thermal non-equilibrium. If you have thermal equilibrium, and molecules want to be in thermal equilibrium. They want to be in thermal equilibrium. So in many cases, if you're at atmospheric pressure, all of the, what drives this? Collisions. It's the collisions that tell the molecules they all want to go to Boltzmann. So if you're a nitrogen molecule in this room right now bouncing around, you have between 10 to the 9th and 10 to the 10th collisions per second. It's those collisions that tell the distribution that you've got to become Boltzmann. If you're not Boltzmann, pressure is on to go back. You get too many, pulls back. So collisions. So therefore, when the collision frequency is high, propensity for a well-defined temperature is high. The place you're most likely to encounter thermal non-equilibrium is in a low-pressure excited gas. If you have a rarefied gas dynamic problem, you maybe take some high-temperature gas, expand it in a nozzle, expand it fast. Pressure goes down, collision frequency goes down. You have what's called freezing. And let's say the vibrational temperature will be, as you're going through the expanding nozzle, the kinetic energy is picking up, the vibrational temperature is going down, and you reach a place where the vibrational temperature can't change anymore. There's not enough collisions. There's still a kinetic temperature for a while, because there's enough collisions to maintain the Maxwell-Boltzmann distribution. But because the energy spacing for vibrational change is so big, it takes too much energy in a collision to make it right. So, if you have temperature, if you start with a temperature, start with a CO that's in level V equals 0, and you excite it, or you put it into a high temperature chamber, it has to wait until there's enough collision that has enough energy to take it from 0 to 1. And the characteristic temperatures 3,000 degrees. You might have to have 10 to the 7th collisions or more. So it's all about collision frequency and energy difference, what you're trying to do. But we use this concept of temperature, which has a real meaning. But when you start producing non-equilibrium, then you have to think about it a little bit more. What does it mean? Then you say, well, I'm an engineer, I got to model this arc jet, or I got to model this nozzle. So you want to stick with the thermal concept as long as you can. So you, well, okay, I'll accept it's not just one temperature, there's two. One for vibration, one for translation and rotation, we usually say are the same. Next is, no, I better let one species have a different temperature than another. So we hang on to the temperature concept as long as we can. It's not real, but it's close. And then if you go to complete chaos, no well-defined temperature, which only occurs in extreme situations, low pressure, high energy situations. It's complicated. Now you have to start modeling the time-changing population in all the quantum states. It just becomes impossibly big. Hope that helped a little bit. So temperature is such a powerful concept. And you see it's in the Boltzmann distribution. It's so powerful for us. Yeah. That's a good question. I think pressure is usually well defined. You think about, you derive it, usually you start with some particles in a box and you can derive kinetic theory and you get P equals NKT sort of thing. But you can imagine, what if you imagine your box now with only 3 particles? What's pressure? I think it only has meaning when you have an ensemble that's big enough to, so that's an interesting question. At what point does pressure become undefined? Well, pressure is coupled back to the velocity distribution function. I think as long as, usually we'll say the last thing to go is the Maxwell distribution. That's the last one to go. Because why? The energy spacing between translational energy states is so close. But remember, a lot of this stuff came from statistical mechanics, which is really large numbers. I think as soon as you go to small numbers, you have to re-ask this question. But, atmospheric pressure, like I just told you, 10 to the 9th collisions per second. That's a lot of collisions. A lot of little molecules bouncing around here. So for that reason, in engineering problems, where the pressures are not low, pressure is defined and temperature is defined. But that's an interesting question. At what point is temperature? Well, I think you'd have to go back to what is pressure? Usually you can talk about collisions with the wall. Probably do it that way. Collisions with the wall, their frequency comes back to the distribution functions, pressure averaged, because they have to exchange, they lose their momentum when they hit the wall. I guess you'd have to go back to a very basic definition of pressure and then ask can't you trust it anymore? Clearly, if you had only a few particles bouncing around in a box, there's no pressure. So I think it all comes about. I never had that question before. That's a good question. Yeah. Yes. Well, we do shock tube research. So shock wave comes along. We think of it, we model it as a discontinuity. It's actually a zone. Shock wave is a zone of, say, 5 to 7 collisions, thick, mean-free paths. 5 to 7 mean-free paths over which kinetic temperature is reestablished. In comes the gas, shock wave is fixed, say. In comes the gas, well-defined, room temperature, here comes the gas. If we can model that as a discontinuity with the shock wave jump equations. But in reality, it took some collisions to reestablish kinetic temperature, translational temperature. It takes more collisions to reestablish the rotational temperature. It takes more collisions. So that's how we study vibrational relaxation. We shock heat a mixture, and we'll watch the population in the different vibrational levels evolve with time and reestablish the Boltzmann. And there'll be a finite vibration. It'll be measured in distance or time. We usually make the assumption that translations and rotational temperature are defined. We treat them as fast. That's how we measure it. We provide a step change in temperature, translational temperature, and then watch the vibrational temperature rise. Eventually they come together. This all has to do with two things: collision frequency and the probability per collision of making a quantum change. In fact, I think I might talk about that a little bit. So it all has to do with the probability. So the bigger the energy level spacing, the harder it is to happen. You make this molecule, small spacing, happens fast. Make it big. Let's say the spacing is 2800 for CO, and the temperature experiment is 1,000 degrees. Well, the energy in the collision, you have to search for that high energy. There's the Maxwellian distribution. And so the collisions are occurring with different amounts of relative energy. You have to seek out those which have enough energy to make this happen. It's all about conservation of energy. You can't have a quantum change unless there's enough energy. So it takes longer and longer as the temperature goes down, but that's how we measure it. In the modelers will do, they'll use this theory, semi-classical theory. It all comes back to, if you take a harmonic oscillator, it comes back to a single probability of going from 0 to 1. If you tell me that, I know everything else. But yeah, that's the way we measure those parameters. And you could do it in reverse. You could do expansion, but I like to do a step change. So we have well-defined time 0. We assume we know temperature, translational and rotational, and we watch the evolution of the vibrational distribution. And what do we learn? We learned, this is interesting, nature wants to have a vibrational temperature. And so what happens in the limit of a harmonic oscillator is that the vibrational temperature is always defined, but it changes with time. So right behind the shock wave, the vibrational temperature 300 degrees, it goes up to the final, but it takes time. But the distribution, somebody asked this question, but if you measure the distribution function, you'll see there is a vibrational temperature. That's an amazing thing. And you can interpret it when you... Yes, yeah. So the shock wave comes along, post-shock temperature is 2,000 Kelvin. Neglect the thickness of the wave. The translation rotation temperature is 2,000 Kelvin. Vibrational temperature is still 300. It has to wait until it has enough collisions to get excited. And it all has to do with the collision frequency and the probability per collision, which depends upon temperature. So basically, a CO molecule needs to be hit by a colliding partner to pump in that quantum. It's got to come in fast. So, but the interesting thing is that you say, well, how do you model that? The interesting is you can show that somehow nature will retain the relative populations in the different vibrational levels that correspond to a temperature, a vibrational temperature. So the nice thing is we can still think about temperature. It's not perfect, but we can infer a temperature, and it'll evolve, and we can measure it. So you can, in an engineering problem, in a nozzle, say, a rocket, you can calculate this problem, but you might say, where do I get those parameters? Well, somebody has to do that experiment. We do that. What?
I do DSMC, so I'm rely on.
Okay. It's interesting. Of course, I'm an experimentalist. The modelers can always fit your data. They find a way. Of course, the trick is you want it. What? Yeah, I should. I'm losing my voice. Okay. Okay. Or somebody could bring me some water. Somebody could get me some water. That would be great. Okay. So we're running way behind. Okay, that'd be great. Yeah. So I'm going to give you an introduction to electronic spectroscopy. All right, so the picture on the right is a plot of the line strength. Remember, there's positions, strengths, shapes. The ultimate absorption is going to depend upon the strength and the number density in the absorbing state. So the strength is a reflection of the Boltzmann distribution, but in electronic spectra, there's lots of options, and lots of choices, and they all get broken down to spectra notation. This is a plot of the line strength for OH, which is an important combustion species, at 2000 Kelvin and for a particular transition. So all this notation we'll deal with. This tells me we're looking at transitions from the ground electronic state to the first excited state between V double prime of 0 and V prime of 0. And these are the rotational states. So we're looking at the distribution over the rotational states. And now you're seeing not only a P and an R, you're seeing a Q. Remember what, though? It's the alphabet soup. P, Q, R. P is delta J of -1. Q is nothing more than delta J of 0. And it turns out that for electronic transitions, you can have a delta J of 0. And they are favored, Q1, Q2. So there's a lot of detail here. This would be something that that's it's buried in the book you've got. There's a summary of a case study. We do case studies. And we'll tell you how we came about this plot. Why do we care? If I want to measure OH at 2,000 degrees, I want to be right here because the absorption is the strongest per molecule. So you need this sort of understanding to pick the wavelength, unless you're just copying somebody else that came before you. So we're going to look at the potential energy wells and the types of spectra and go through the analysis, which separates into rotational. This is rotational here, rotational and vibrational analysis. We'll talk a little bit about dissociation energies. So this is the figure I showed you earlier. This is 3 of the electronic states of nitrogen, the A, B, and C states. There's many more at different levels. X is not shown. It's below the plot. And when you pass nitrogen through a plasma, you will see emission associated with these systems. And the nice thing about this is that both homonuclear and heteronuclear molecules have this character. So the first positive system is the of nitrogen is all of the transitions between A and B. So all of the transitions between states A and B comprise the system, and there's a lot of them. You might ask, how do you ever figure all this stuff out? Well, you know, it's detective work, little by little. You know, you read the literature and you find out how other people have sorted it out. Each molecule has its own unique spectrum. They're all different. Trouble is, a lot of them overlap, and that makes it a challenge. But nonetheless, you can think of them separately. Now, we talked about the potential and the attractive forces. So the 2 nuclei come together from out here, come traveling in. Now they begin to be attracted, and they go faster and faster and faster, and they go slower, 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 and they go back out. What happens if there's a collision during that time? If during this 10 to the minus 13th second round trip or so, there's a collision. Remember, the collision frequency might be 10 to the 10th, so it doesn't always happen. But if there's a collision, on average, some energy is going to get transferred. And this particle, these 2 particles, will lose the energy required to escape this well and get trapped. So, because there's lower potential energy down here. So if there's a collision sometime in this short period of time, molecules are going to get trapped in this well and stay there. Okay, so the restoring force, you know, the potential, the equations for energy, derivative of potential with distance. As you change the electronic configuration, so in other words, you have a set of electron distributions set by quantum mechanics. And there's the ones that have the lowest potential energy. Now I take one of those electrons and I park it in another allowed state that changes the overall electronic energy and pushes it to a new level. Each one of those allowed configurations has a different energy area, has a different energy, and it's usually measured by at the bottom of the well. So as you change electronic energy, the bottom of this well moves up to different levels. Now, we can begin to sort out all the things that can happen by looking at these two cases. So here we have a ground state and an excited state. Notice how the RE is different than this one. What does that mean? It means the moment of inertia is different. It means B is different. It means the line spacing is different. So all of a sudden you begin to see the elements that you might use to ferret out the spectrum and figure out what's going on. DE is the dissociation energy relative to the bottom of the well. DE prime, this would be DE double prime. TE is the energy between the bottoms of the wells. There's a lot of numbers on here. This E excitation, that would be the difference in the energy of the atomic partners when they go away. Apparently, this one here, the partners that represent this well, when they're apart, they have a different electronic configuration. That's called the atomic excitation energy. So all of these numbers and conservation of energy come into play as we look at the spectrum. So there's some terminology. Use X to denote the ground state here. Use A to denote the first excited state. Strictly speaking, use a capital A for the first electronic state that has the same spin. If the spin changes, you use the lowercase. So there's a lot of rules, and the trouble is that the rules are not always honored, but there's a lot of rules. So if you look at the spectrum, you can see how you might begin to infer these energy differences. There's several here, and you can begin to see how you might be able to sort these out. So for example, I might look at, if I could look at the spectrum and I can see the minimum, if I look at a place in the spectrum, I might be able to identify this one here. And that would correspond to the TE and the slight differences in vibrational energy. So there's ways to sort out the spectrum. I'm just going to quickly zing through this. D is the dissociation energy, not the distortion constant. Okay, there's some nice questions that had to do with collisions. And so one way to think about a lot of these problems is to think about characteristic times. Electrons are moving fast. And so they can change orbits in a very short period of time. So you might be able to change the orbit in a time of, say, 10 to the minus 16 seconds. So the electron zings to the new one. The thing is, that time is quite different than the characteristic times we might have for other processes. So for example, the characteristic time for one vibration is about 10 to the minus 13 seconds. The characteristic time for one rotation might be like 10 to the minus 10. That's interesting. It vibrates 1,000 times for one slow rotation. And both of those things are very slow compared to the time to excite an electron. The collision time, that's the time, the duration of a collision. They come together and that interaction lasts about 10 to the minus 12 seconds. So there's all these characteristic times. So if you look at a problem, you might ask, what do I want to know about? Is this something that happens on a very short time, or can I kind of average over long times? You can sort out what you want to do is model the dominant process and make assumptions about those you can approximate. So these times come into play in helping us think that through. Now there's a new number, the radiated lifetime. If I park an OH molecule in an excited state by the absorption of a photon and I leave it alone, no collisions, it will spontaneously emit back. But because one more thing about quantum mechanics, I can't tell you exactly when it's going to happen. Quantum mechanics is about probabilities and uncertainties. But on average, it will emit again in something like a microsecond to a nanosecond. And we'll talk about this a little later. So there's a lot of characteristic times, but this is the one that's kind of reminds us of quantum mechanics again. You can't specify the exact, you can only specify the probability. So because this electronic time is so much shorter than everything else, that means that this molecule is vibrating and rotating, and suddenly the electron changes. That time is so short that there's no change in the vibrational in the internuclear spacing. It's frozen in time so fast. That helps us model things. Okay, now molecules vibrate. And so let's say we might have a molecule that has this much energy. It goes back and forth here. The potential energy is the maximum is fixed. As it goes down in the well, it exchanges with kinetic energy. Now, the quantum mechanics will also tell us where does the molecule spend most of their time, and it will tell us that they spent most of their time while it's turning around. So from a probability point of view, the molecules are longer at the turnaround times than they are anywhere else. What does that mean? That means that there's a higher probability that exists between turnaround points and other turnaround points. They have more chance to match in time. That turns out to be an approximation that we can use. Now, let's see. We were talking about how long does it take to excite a molecule vibrationally. It's interesting. So it turns out that the most efficient excitation for vibrational excitation is when the duration of the collision starts to match the oscillation time of the molecule. So when the molecule is kind of oscillating 10 to the minus 13 seconds, if the collider comes in and this interaction takes place over about the right amount of time, it's more efficient. That's called semi-classical theory. So people have figured that out years ago. That those are the ones that are going to be most efficient. Okay, now we have discrete spectra and what do I want to call it? I'm going to talk about discrete spectra first. So if we have the bottom of this well is the same as this one, that means if the REs are about the same, it means their moment of inertia is about the same. If they're like that, then you can, the Frank-Condon principle, that's the principle that says that the transition takes place on a vertical line. In other words, if you assume that the electronic time is 0, then, and that the molecules want to go from where they most often are to another place they most often are, then the strong transitions will be those which correspond to endpoints. And where that endpoint is, I go from 2 here to 1, depends upon the wells. And those little wavy forms are estimates of probabilities in terms of time or time spent. They're just kind of schematics to show you that the wave mechanics is coming into play. So if you're in vehicle 0, you're on average, you're mostly in the middle. If you're in the others, you're nearly always on the ends. And that, coupled with this Frank-Condon principle, tells us which transitions we're most likely to see. And whereas we had simple selection rules for V and J, now they're going to get more complicated because you're going to be favored by the alignment of these vertical positions. They're called the Frank-Condon factors. So we can look at some possible cases. Here's a case. So I said we have two kinds of spectra. We have discrete and continuous. So now, if you measure the spectrum, and this is absorption coefficient versus, say, frequency. Nothing happens. Suddenly, at nu 0, something starts happening. You must be getting close to this energy right here. If you think that all the molecules are kind of down here, the minimum energy is that corresponds to V equals 0. And it'll be reflected in kind of a noisy looking spectrum. Now, at some point it will turn to continuous. Why does it turn to continuous? Because the energies are enough to actually get above the dissociation energy. So the pattern of the spectrum allows you to begin to infer energies. Remember, I told you I only need 4 parameters for rho vibrational. Now, electronics is more complicated. We got all these different term energies, and it's more complicated. But you can still sort it out if you have spectra like this. So there's a continuum case, which I just showed you, where we would look for the initial frequency and the transition to a continuum. And there's a repulsive. Now there's a laser called an excimer laser, and so not all molecules have potential energy wells. Sometimes you bring atoms together that don't like each other. Instead of attracting, they repel. They only repel. Come together, no, they go back. And that's because the quantum properties of these two atoms are not compatible. The spin, usually. So there are molecules of this type, and there are lasers that are based upon this concept. But if you have this concept, what that means is that you'll have only a continuous spectrum. There's no discrete capabilities. There's only a continuum of states up here. So just what the spectrum looks like begins to tell you quite a bit already. Here's the picture I showed you earlier. This is the one that they take in my lab. And so, I asked them to figure out this stuff and identify these states and so on. Remember, but this is with a cheap spectrometer. Therefore, this is what you see if you have very bad glasses. If you have good glasses, oh, now you can start to see the discrete nature. But you have to have an instrument that's capable of doing that. Okay, so we're going to see a spectrum, and we have to interpret it. There's the rotational distribution, there's the vibrational distribution, and then there's this question about which electronic states are you working with. So a lot of the effort goes into, once you figured out the electronic states, you're probably reading somebody else's paper, not figuring it out yourself. Once you figure out the electronic states, then you're looking for the vibrational distributions, and you're looking for the rotational distributions. And the hardest part by far is the rotational part. So I always go back and we use the notation T for the total energy. It's the sum of the electronic, vibrational, and the rotational. We always use F for rotation, G for vibration, T electronic for electronic. So the distribution or the spectrum is based on the difference between T prime and T double prime. So you write out these expressions and you take the allowed differences and you begin to see where all the lines, what do they look like. And one way you can figure all this out is by looking, someone mentioned, why don't you just measure the whole spectrum and infer temperature? Well, you measure the whole spectrum and you look at it and you can infer the parameters we care about, which are, we're back to B again is a primary one. So if we're looking only at the rotational distribution, it's B's that we're worried about. But now, because the potential energy wells can be quite different, B can be quite different, and the spectrum changes dramatically. So I'm going to have to go a little faster than I'd like to go, but you always take the difference between the upper state and lower state. And if I'm looking within a given band, only J is varying. So I look at those distributions, and I recognize there's a variety of different M's. Someone asked, why is the R branch a little higher? You start seeing it here. In the R branch, if you let M, a number, be J plus 1, and in P branch you let it equal minus J, you get you plot these out, it's called a four-track parabola. And this is kind of, that weighting factor is recognizing the Honda-London factor that I mentioned that explains the ratio between the R and the P. Now, here's an example. So whereas the B values vary only slightly when you go up in J, they vary only slightly when you go up in J. They can change a lot when you change the electronic states. So for example, if I look at the ground state of O2, X tells me it's the ground state. We'll talk about this notation later, called the term symbol. B is 1.44. In the upper state, it's 1.05. So now if I use my model here for how you find the band head, which is based upon this difference here, when this difference gets big, the band head can occur at a really low place. Band head occurs at M of 3. That just means you don't have a couple lines and it's a band head. Quite different than the rho vibrational. So the way we do this, you look at the spectrum and you measure the positions of all these lines in frequency space. And those were 20,000 wave numbers. So who knows what the wavelength is? 500 nanometers. So 500 nanometers. So basically, this is what you see at 500 nanometers. And if you plotted the positions using my trick of using M to represent, in the R branch is M plus, M is J plus 1. And the P branch is minus. You get this continuous curve, which you can fit. And what are the fitting parameters? The B's. And of course, there'll be some lines missing. So there's some steps, and I'm just going to show you one example of this. There's some steps of how you do this rotational analysis. There's a rotational analysis, there's vibrational analysis. We're within one electronic transition. We sorted it down to one vibrational transition. We're looking at the J distribution. But there's some steps, and I've laid it out in my notes precisely. And so if you see a band head, you'll know what's happening. You'll see a distinct little sync place, but you won't know what J is. If there's no band head, you'll see a null gap. That means you determine this rotational, this vibrational frequency. So it all depends upon whether you see a band head. If you see a band head, which is common, you start from the wings, which is where the spacing is big, and you work your way back in. And I show you just quickly how you do this. And remember how I showed you about the first difference and the second difference. If you take the difference between the energy levels, that's the first difference. That's the wavelength of the transition. If you take the second difference, it's the difference between the adjacent lines. It's the change in the spacing. So basically, here's an example that I use in my class, which I borrowed from somebody else. But this is the spectrum for chlorine. This is an electronic transition from X to A. We'll deal with the symbolism later. But anyway, this is these are the group of lines that you see. And this is 18,000, so it's around a little over, 500 and something nanometers. And the physicist goes in, he measures the positions of all these lines. That's all we have. It looks like this. Here's the band head. Tabulated like this. We're going to interrogate the tabulation and infer. What are the parameters we're after? The B's. There's two B's. B prime, B double prime. And we have to find out. That's called rotational analysis. Now, and from those, you can also infer once you have B, of course, you have the REs, and you have the null gap frequency. So here it is again. There's the band head. Well, we're going to find out that's the null gap. That's yours, not mine. Okay, good. So you go all the way out to the wings here, and now you take this difference. And if life is good, that's the spacing between those two lines. And if I do it again, I get a number that's different. And that's different by second difference. So if you're lucky and you're out there, I've just determined that these spacings are diminishing by a constant amount. This is basically the same number. And so if you keep doing that, you can work your way in, and you're going to work your way in, and you're going to find the null gap, and you're going to identify the J's. It's all based upon this idea that T2 is a constant. But T2 can be plus or minus depending upon the relative values of BV, B prime, and B double prime. So because we're so short of time, I'm not going to belabor this, but you can work your way up. You don't know yet which J this is. You don't know yet which J this is. But I can go up. I realize I'm down one, down one, down one. Now I've got to go all the way to here to get to the next one to maintain this 0.17, 4, the 3. I don't yet. Eventually, there's no line. It's missing. I just found the null gap. And then I count backwards and say, well, then this one down here is 9. So you use the principle of constant second difference to find your way up and to find the null gap. And then you keep going and turn around the bend and come back down. And therefore, I have measured T1 and I've measured T2. And I can solve for, I measure the null gap right here. Yeah. And T turns out to be negative, is this 0.17. I averaged them all. And therefore, they're all negative, and that tells me that since A is this number right here, here's the minus, I've just found the difference between these two. So now I've got delta B. I've got mu 0 and I got delta B. I'm now to get B double prime or B prime, I use the method of common upper states. I identify the P2 line and the R0 line that have the same upper state. See, this goes from 0 to 1. This one goes from 2 to 1. And so I take those numbers, and that difference is 6B, and I just solve for everything. So you can use this principle. This is rotational analysis of electronic spectra, from which I get the null gap value. I get B prime, B double prime. So it's like a step-by-step, you interrogate the spectra. Now, if you look at emission, if you use emission, you're starting from an excited state and you're coming down to a family of lower states. Emission, you're probing the distribution of the lower states, the quanta, the spectra, and vice versa. So emission gives you one thing, absorption gives you another. So imagine I'm in a given quantum state and I look at the absorption spectrum. I'm going to different upper states. So absorption allows me to interrogate the parameters for the upper states and emission of the other. No, okay, that's like a 5-minute explanation for rotational analysis. That's a lot. There's vibrational analysis. Vibrational analysis says that if I look at the spectrum, I have to recognize that there's a variety of different B double primes and V primes. And if I do that null gap analysis that I just did, I can make entries into this table. It's called the Deslandres, excuse my French, the Deslandres table. I guess he did it first. And so you look at the spectrum and you find all these null gaps and you enter those numbers here, wherever they are. Then you go back to my anharmonic oscillator expressions that I talked about earlier, and I recognize these first and second differences. So this concept of first and second differences allows you to sort out all the spectra and get the parameters that you need. So if once I get do the experiment to get some of the entries in this table, I could go along this row. Now, going along this row, I'm probing V double prime. I go along this column, I'm probing B prime. So those numbers change in a way that's very understandable. So use first and second differences, and you can sort this out. That's a common problem. It's usually a couple homework problems in my class and always on the final exam. So here's some examples. So we have some molecule, I don't know what it was. We make all these entries. And you take the first difference, first difference, first difference. First difference, first difference, first difference. Now what? Take the second difference. And it's a constant. So I've got everything I need to sort out the parameters in this problem. So you can do rotational analysis, vibrational analysis, emission analysis, absorption analysis. You analyze the spectrum and you can always get all the parameters you need. Or if they're known, you can calculate the spectrum. That's the more common situation. So just a quick story again. You use this transition between continuous and discrete. You have to find band origins. You have to find, there's only a few parameters in this problem. There's the TEs, the dissociation energies, the vibrational energies, the omega EXE, VE, and alpha. A lot of stuff. Okay. Now, that's something simpler. If you do thermochemical calculations, you care a lot about the heats of formation and the dissociation energy of a molecule. How do we get the dissociation energy? Well, we might get it from the spectrum that I just showed you, the dissociation energy. When I was a graduate student, a long time ago, the literature had two values for the dissociation energy of nitrogen. Imagine that, nitrogen. We must know that to 3 significant figures. There was 2 camps. One was 7.5 eV, one was 9. It was amazing. Eventually it's resolved by spectroscopy, but there were issues. So the point is dissociation energy is really important. Why? Because if you're doing thermochemistry, to calculate the proportion of O2 atoms that are dissociated, it depends upon temperature and the dissociation energy. Actually, it depends on pressure too. So dissociation energy is really important. If you want to produce some oxygen atoms, you have to dissociate the oxygen molecule. So if the dissociation energy is big, it makes it harder to do. So there are experiments to infer the dissociation energy, and there's a real simple one called the Bird-Spooner method that I'm going to tell you about. There's a couple different ways to get at the thermochemistry. This is a reminder here that you can have this. This is a stable ground state. Here's a stable ground state. Here's a repulsive state. When states cross in energy, molecules can go from one category to another, called curve crossing, and that'll affect the spectrum. So, for example, we might see a spectrum that looks like this. We might see one, if we go up in frequency, we see discrete, goes continuous, and then it goes away. And we can interpret this in terms of these parameters to try to solve for everything. And we might put, if we want to find the G's, we put that in this Landry's table and so on. So I'm going to move faster because, okay. Again, this is how people used to do it 100 years ago, film. And then people would laboriously figure out what are the quantum states, what are the transitions, what are the, remember there's only so many parameters in this problem. Once you determine those parameters, you're done. And that's what the atomic and molecular physicists did. Here's the NO gamma bands. Those are electronic transitions of nitric oxide. 0 to 0, and here's the wavelength, 2269 is in the UV. This is 2370. That's a longer wavelength, which means a shorter energy. And so this tells me that this is between V double prime of 0, V prime of 0, V double prime of 0, and vice versa. So this is a delta V of 0, 1, 2, and so on. So people figure all that out. Now, what are some alternatives? We ran into this problem a few years ago. You can use thermodynamics, like a calorimeter or something to get some data, or you can use kinetics. But there's this very interesting Spooner method that's, I think, helpful. This idea is that whatever the atomicity is, it's a constant. So that just says that if you go to this energy expression for G, if you assume that this analysis holds, I can get the delta G, the difference, the change in G, and it's a constant plus, so it's a slope thing. It's a constant plus something proportional to V. So delta G is AV plus B. So that means that if I have a molecule that looks about like this one here, diminishing energy spacing, where delta G, I can plot delta G, and delta G gets smaller and smaller and smaller and smaller, it goes to 0. The approximation is made that this is a linear slope. When V is 0, this is just G1 minus G0. And as you go up in V, the delta goes down. So you can then say that the dissociation energy is given by this simple result. It's just B over A. So you can solve for the dissociation energy this way and relate it back to omega E and XE. So there's a way to get dissociation energy from the slope of this, distribution. So now you're going to have to measure delta G over a few different V's, and then you extrapolate. The question is, how good is this very, very simple thing? Turns out it's not great. It's the area under the curve. Okay, in reality, it's not linear. It actually gets smaller and smaller and smaller. It falls off. Here's an example. For HCl, if I do this, I get 513 kcals. And the maximum V is 27, but the answer is 427. So it's only good to about 20, 25%. But it's simple. It's easy to think about. How about the dissociation energy? So if you do combustion, you have to know how to do thermochemistry. You have to, if you wanted to calculate the proportion of iodine atoms, homework problem would be, imagine an iodine cell, pressure is X, temperature is Y. What's the proportion of iodine? That's a classic homework problem. So what does it depend on? It depends on the dissociation energy. So therefore, if I measure I can determine the dissociation energy. So for example, it's the equilibrium constant, and this would be for, if you've had thermochemistry, you would know that the equilibrium constant for pressure, pressure units, is the partial pressure of the products to the stoichiometric coefficient divided by the partial pressure of the reaction on the left. So K sub P, which is a function of T, is given by this ratio. And you also know something called Van Hoff's relation, if you had thermochemistry, that the derivative of log K with T is delta H of RT squared. Delta H is the enthalpy of reaction of the products on its reactants, which is dissociation energy, plus the sensible enthalpy of the products minus that of the reactants. So what does that mean? It means if I measure PI and P2, I've just determined KP. And if I do this at two different temperatures, I've just determined this quantity. And if I can estimate these, I've just determined the dissociation energy. So that's how it's done. It's quite good. So measurements of partial pressures can lead you to heat of reaction and dissociation energy. And how do we do that? We measure these things spectroscopically. So we measure the partial pressure, mole fraction, by laser absorption, solve for K sub P, do it at a couple temperatures, implement Van Hoff's relationship, and we solve for DE. This was another interesting problem. So this was about maybe 12 or 15 years, 12 years ago, 15. I was given, my students wanted to learn how to measure OH in a shock tube experiment with laser absorption. Okay, go out and show you can do it. And I always ask them to measure something where we know the answer. And for years, the students would measure the time history. They'd measure the time history of OH in a hydrogen-oxygen mixture at known temperature, which we got from the shock speed. So we know the pressure, we know the temperature, we know the initial concentration. The question is what happens? Well, OH forms. And if you calculate with the detailed chemical model, the OH forms and then it plateaus. That's called the partial equilibrium region. That concentration should depend upon the heat of formation of OH. And for years, the students would only get within about 5% of the right answer and would say, okay, good enough for now. Finally, this student was very careful. He said, I don't understand. We tried everything. What's wrong? We were getting a number that was 5%, or a few percent different than in the literature. Well, someone's wrong. We thought it can't be us. Those thermochemical people must know more than we do. But it turns out that we were using the GRIMEC, it's called GRIMEC, the thermodynamic database that was in GRIMEC. And in order for us to fit our data, we had to change from 9.4 to 8.9, yes, say 5% or so. Hard to believe that heat of formation of OH is not known better than that. Darn, if it didn't turn out that, turns out that somebody at Argonne National Laboratory was computing these things. He calls it, he has a name for that, active thermochemical tables. Turns out he discovered also that they need to be changed. So there were, anyway, happy story. Turns out that we were measuring a new number, which was consistent with his new number, and so that's just an evolution. So just like I told you, the dissociation energy went from some people thought it was 7.5, it went to 9.7 eV. And similarly, so over time, thermodynamic parameters get better and better and better. How do they get better? If you look into thermodynamic databases or the enthalpy or products of species in tables, where do you think those numbers came from? Most of them came from spectroscopy. Some of them are calculated. They weren't measured. I mean, they weren't, the numbers in the table weren't measured. Spectroscopic parameters were measured and used to calculate the tables. But one of the important, so that you know, or now you know, it's about BE and alpha and omega E and XC and the dissociation energy. So over time, these numbers get better. They aren't set in stone. They're getting better and better and better. So those are two examples of the nitrogen dissociation energy when I was a graduate student, and now the thermochemistry of OH. So you have to remember these numbers are not two things. They're not perfectly known. You might think they are. Like rate coefficients, they're not well known yet. They're not perfectly known, and most of them come from spectroscopy. Okay, I think I caught up. My voice is back. So I've gone, I got some questions, which I appreciate. Covered a lot of ground on purpose. You've seen a lot of stuff. You can decide if there's anything here that interests you. Come see me if you have questions. And what I've tried to show you is it may seem like spectroscopy is a little complicated, but all of my students are mechanical engineers. They come in, they don't know anything, and they go out and they measure things. So you can go a long ways without even ever taking a course in quantum mechanics. You can take it. Most of my students do, but you don't have to. It's all about line positions, strengths, and shapes. We're focusing right now on positions. What's the interpretation of the spectrum? Where are the lines and why? Now, the next thing we're going to worry about, well, first we're going to talk about bigger molecules. Somebody asked about bigger molecules. We'll do bigger molecules quickly. And then we'll start getting into the equation of radiative transfer. How do you relate absorption back to the number density of species? That introduces what's called the Einstein factors. You have to introduce some new theory. But it's not that bad, really. I think this is about as hard as it gets right here. Okay, I think we're done. Any questions? Yeah,
When you have the bandwidth in the P branch,
yeah. It can be in either the P or the R.
yeah, so when we have it in the P branch, how can we physically explain that? Does it mean that the D prime will be larger than D double prime? So as you increase the vibrational level, you are having a smaller
So you remember when we did the rotational stuff, it gets bigger in the P branch. The line spacing gets bigger in the P branch and smaller in the R. Now so the band head could be either in the P or the R, and it's just a question of the sign difference between B prime and B double prime. And I never remember which way to do it. I can't answer your question.
Yeah, but in the P branch, it's written that the D prime will be larger than D double prime.
Okay?
So, I mean, physically possible that while you increase the vibrational level, you are having smaller.
No. It's all about the location of the minimum of the potential energy well. If it's at a bigger value of R, then it's got a bigger B and a bigger moment of inertia and a smaller B. If, on the other hand, the well is to the left, if the lower one's here, the upper one's here, it's just a question of whether the minimum is at a lower or bigger. It could be either way. Yeah, so the band head is always in the R branch for rho vibrational, but it can be either the P or the R side for the electronic. And it's all about the signs of B prime and B double prime. Yeah, good. Anything else? Yeah, go ahead. Yes. Yes. Yeah. Okay, so basically most people have common, so certain molecules are are the reference molecules, like nitrogen, hydrogen, okay, and they're zero when they're molecules. Personally, I like the reference system where it's all atoms. That's just the way I like to think about it. You get to pick wherever you want it to be, as long as you just have to be very consistent. So in the Boltzmann ratio, you have an exponent in the numerator and you have one in the denominator. You just have to be very careful that you use the same zero in referencing the partition function and in the energy of the state. And that's where you can get into trouble, because there are approximations for the partition function, and people use the ones that have a different reference. So, I think it's like sea level. You can call it sea level, but, somebody could decide they want to have it reference to Mount McKinley or something. It's just... Because you're usually interested in delta. I mean, it's always about delta. Heat's the formation is the difference between the products and the reactants. They're both going to go up. It's the difference. So I'm just telling you that I'm aware of people stumbling on this trivial problem, really. Because you can approximate the partition function by taking the product of the partition function for rotation, vibration. It's an approximation. Strictly speaking, these energy levels are slightly coupled. But then you want to be precise about the energy level of the state in the numerator. And that's where people get into trouble. It's always okay to approximate something, but you don't want to approximate the thing you care most about, which is the position of this line or the energy of that state. So, I'm sorry I ran over. Hope it was worthwhile.